Yeah, let's start the meeting.
Yeah.
Yeah.
So
So,
welcome to the third
welcome to
session
the third
on
session
phase
on
transformation
phase
in
transformation
materials.
in
So
materials. So,
uh,
uh,
previously we had
previously we had like
two sessions,
two
and
sessions,
we discussed
and
like
we
basic
discussed like
thermodynamics
basic
and some
thermodynamics and some
GVS composition,
GOS composition, like
pre-reduced composition phase
pre-reduced
diagrams.
composition phase diagrams.
So
So,
I will be continuing
I'll
them.
be
There
continuing
are
them.
few
There are
phase diagrams
few
that
phase diagrams that
I haven't discussed
I
in last
haven't
session.
discussed in
So
last session.
I
So,
will cover
I
those
will cover those uh,
in today's session.
in today's session. So,
Let me check whether
let
I'm
me check
recording.
whether I'm recording.
Okay, so
Okay,
let's start.
so let's start.
So
So,
let's first
let's first
derive what is
derive what is the
Gibbs phase rule,
Gibbs
because
phase rule, because
in
last time
last
we have
assignment
in
also we
last
have
assignment
used the
also we
Gibbs
have
phase
used
rule.
the
So
Gibbs phase rule. So, uh,
yeah, in
yeah,
previous sessions
in
or
previous
in
sessions or in
lectures,
lectures, sir, or either sir or me
derive
didn't
anything
derive
about
anything, right?
the
So
Gibbs phase
about
rule.
the
So
Gibbs phase rule. So
let me derive that
let me
here.
derive that here.
So
So
as you all know,
as you all
the
know,
Gibbs phase
the
rule
Gibbs
number
phase
of
rule,
degree
number of
freedom is
degree
equal to
freedom is equal to
F is equals
F
to
is equals to
C
C
minus P
minus P
plus 2,
plus 2,
right?
right?
So
So
this was
this
the Gibbs
was
phase
the
rule.
Gibbs phase
We
rule.
know,
We know,
right? So how do we
right? So
derive it?
how do we derive?
We came
We
from
came from
F equals to
F
number of
equals
degrees
to
of
number of
freedom,
degrees of freedom,
number of
number of
degrees of freedom.
degrees of freedom.
C is for number
C
of
is for number of
components.
components.
P is for number
P
of
is for
phases,
number of phases.
and 2 is for other
And 2 is
variables,
for
which is
other
the pressure
variables, which
and
is the
temperature,
pressure and temperature,
right?
right?
So
So
to derive this Gibbs
to
phase
derive
rule,
this
now
Gibbs phase
we
rule,
need to
now
know
we need to know
if
if
we define a
if we
system,
define a system,
right?
right?
We need to understand
We need to
what are the
understand
different
what are the
parameters that
different
affects it.
parameters that affects
The
it,
first
right?
one is
The first one is
pressure.
the pressure.
The second one
The
is
second one is
temperature.
our temperature.
The third one is
The third one is
the composition.
the composition.
Now,
Now,
let's say our
let's
system
say our
has
system
C
has
components,
C components,
P number of
P
phases,
number of phases,
right? And
right?
also it
And
depends on
also it depends on
pressure
pressure
and temperature,
and temperature,
right? So there are C
right? So there are
components and
C
P
components
phases,
and P
and it
phases,
has
and it has
each component has a
each component has a
composition X,
composition
I
X,
in each
I
phase,
in each
in
phase,
P1,
right? In P1,
in PI,
in PI.
right? Now we to
Right
know
now, we to know
to
not
define the
to
degrees of
define the
freedom,
degrees
we
of
need to
freedom.
know all these
We need to know
parameters,
all these
right?
parameters,
So
right? So
number of degrees of
number of
freedom
degrees of freedom
initially,
initially.
I'm writing it for
I'm
initially.
writing it for initially.
I'm not applying
I'm
any
not applying
assumptions
any
or any
assumptions or any
equations here.
equations here.
Initially, how
Right?
many
Initially,
components
how
are
many
there? C,
components are
and
there?
how many
C,
phases are
and how
there?
many
P.
phases are there?
Now,
P.
how many degrees
Now,
of
how
freedom?
many degrees of freedom?
C cross P.
C cross
Do
P.
we really need
Do we
to
really need
have that
to
many
have that
terms
many
or
terms
that many
or
variables?
that many variables?
No. Why?
No. Why?
Because, for example,
Because,
if
for
I take a
example, if I
phase,
take a phase,
if there are
if there are
three phases, right?
three phases, right?
Suppose I'm talking about
Suppose I'm
phase
talking
P1,
about phase
and
P1,
it has
and it
C
has
components,
C
right? Every phase
components,
has
right?
C
Every phase
components. For
has C
example,
components. For example, if
every
we take
phase has
every
all the
phase has
components,
all the
C
components,
components,
all
right?
C components, right?
So
So
P1
P1
P1 has
P1
C
has a
phase,
C
C number
phase,
of
the C
components.
number of components.
Each
Now,
component
each
has a
component
mole
has
fraction,
a mole
right?
fraction, right?
Each component has
Each
its own
component has its
composition.
own
Now,
composition.
if we
Now,
know
if we know
C minus one
C minus
component's
one
mole fraction,
component's mole
then we
fraction,
can derive it.
then we can
Then we
derive it.
can
Then we
easily
can
find what
easily
is
find
the
what is
last
the
one, right?
last one, right?
Or we can call it as
Or you can
xn.
call it as a
So,
xn.
for
So,
example,
for
if
example,
we know
if we know
all the components
all the
composition
components
from C
composition
to
from
Cn
C
minus
to
1,
Cn minus one,
then
then
we can
you can
Cn will be
Cn
equals to 1,
will be equals to 1,
right?
right?
So because
So because
mole fractions,
mole fractions, all the components mole fraction will sum, if
sum all the
we
mole
sum
fractions,
all the
it
mole
will turn out to be
fractions,
1.
it will turn out to be
So
1.
all you need
So
to know is
all you need to know is
n minus 1,
n minus 1,
and the last one
and
you
the
will
last
eventually
one you
find
will
it.
eventually
So
find it.
there is no
So
need
there
to
is no need to
find this Cn.
find
You
this
will
Cn.
directly from
Directly
you will
from
directly
method.
get
You
from
will directly get
mathematically
from
knowing this
mathematically
equation.
knowing this equation,
So
right? So
now from
now,
this
From
This
this,
is first one.
this is first
Now
one.
where do we
Now
arrive?
where do we arrive?
We only need to
We
know
only
C
need to
minus
know
1.
C minus 1, P.
Right, so these many
Right? So
variables are
these many
required.
variables are
Now,
required. Now,
what happens if the
what
system is at
happens if the
equilibrium?
system is at equilibrium?
Right?
Right? So
Suppose if my system
suppose if my
is in
system
equilibrium,
is in equilibrium, right?
let me write it
Let
that
me write
second
it that second
point. Second point
point.
is
Second
number of
point
degrees of
is number of
freedom
degrees
equals
of
to
freedom
C
equals
minus
to
1
C minus 1
cross P.
cross P.
Isn't it simple?
Isn't that
Now,
simple? Now,
if I know
if I know
if my system is at
if my
equilibrium,
system is at
let's say
equilibrium,
I have
let's
two
say I
phases,
have two phases,
which has
which
P1,
has
P2,
P1,
and
P2,
if these
and
two
if these two
are at equilibrium,
are at
then the
equilibrium,
pressure
then the pressure
in both
in
will be
both
same,
will be same,
temperature
a
will be
temperature
also the
will
same.
be also the same.
What about the chemical
What about the
potential?
chemical
Chemical
potential?
potential, let's
Chemical
say
potential,
there are
let's
two
say there
components,
are two
mu A,
components, mu A,
A and B.
A and
Then
B.
mu A in
Then mu
P1
A in
will be
P1
equals to
will be
mu
equals
A
to
in
mu
P2,
A in P2.
and mu
And
B in
mu
P1
B in
will be
P1
equals to
will be equals
mu
to
B in P2.
mu B in P2.
Right?
Right?
So one,
So
two, three, four.
1, 2, 3, 4.
When coming to the
When coming
composition,
to
we
the
only need to know
composition, we
two
only need
variables,
to know two variables,
right? Because
right?
the
Because
other variable will
the
be
other
equal.
variable will
We
be
don't need to
equal.
find
You
it.
don't need to
So
find
the
it.
same goes
So
for
the
if we
same
have
goes for if we
n number
have
of
n
systems.
number of
Suppose A,
systems.
B, C,
Suppose
D,
A,
and
B,
then goes
C,
on.
D, and then
A,
goes
B,
on.
C, D, and then
A, B,
goes on.
C, D, and then
So
goes on. So
phase three.
phase 3.
Suppose if they have
Suppose
different number
if
of
they have
phases,
different
right?
number of phases,
So if
right?
there
So
is
if
P3
there
and
is
P4,
P3 and
then you
P4,
don't need to
then you
find
don't
what
need
is
to
the chemical
find what is the
potential of
chemical potential of
A in P3,
A in
because
P3,
at equilibrium
because at
it equals
equilibrium
to
it will be
chemical
equals
potential
to
of A in
chemical
P1.
potential of A and P1.
So you only
So
need to find
you
two
only need to
variables.
find two
Now
variables. Now
coming to
again,
here,
coming to here,
3.
3.
What this will turn out to
What
be?
this will turn
C
out to be?
minus 1
C
cross
minus
P
1 cross P
minus how many times
minus
we need
how
to
many
subtract?
terms we need to subtract?
Suppose there are P
Suppose there
phases,
are P
then
phases,
we
then
only need to know
we
P
only need to
minus
know P minus,
C
okay, there
components,
are
right?
C
So
components,
there are
right?
C
So there are
components.
C
We
components.
only need to
We
know
only need to
P
know
minus 1
P
phases,
minus 1
right?
phases,
Because we only
right?
need to know
Because we
one
only need to
phase
know one
chemical
phase
potential.
chemical potential.
We need to know one
We need to
phase
know one
chemical potential
phase
of a
chemical
component.
potential of a
Then we
component.
can find
Then we can find
all the chemical
all the
potentials
chemical
of that
potentials of that
component in all other
component
phases
in all
because they
other
are all
phases
just
because they
equal.
are all just
So
equal. So
then that will be
then
equals
that
to
will be
C
equals
times
to C times
P minus 1,
P minus 1,
right? Now,
right? Now,
what are the other two
what are the other
parameters?
two
Pressure
parameters?
and
Pressure
temperature.
and
What
temperature.
is 1 plus 1?
What is
2.
1 plus 1?
You are
2.
right.
Yeah, you are right.
So C cross
So
P
C
will be
cross P
CP
will be CP
minus 1 cross P
minus 1 cross
P
P, P
minus CP,
minus CP,
no, minus into minus
no,
plus,
minus into minus
plus
plus,
C
plus
1
C,
plus 1
1 plus 1, 2,
plus CP minus
plus
CP
CP
cancel.
minus CP
So
cancel.
number of degrees
So
of
number of
freedom
degrees
equals
of
to
freedom
C
equals to
minus
C
P
minus P
plus
plus 2.
these are gives different
This is how
equation,
gives given equation,
right? Now let
right?
me give an
Now let
example.
me give an
For
example.
example,
For
if
example,
this is my phase
if this
diagram
is my
of
phase
water,
diagram of water,
right? It is not
right?
exact,
It
but
is not
please
exact, but
bear with me.
please bear with me.
So this is
So
my pressure,
this is my
this is my
pressure, this
temperature,
is my
and there
temperature,
are three
and
different
there are three
phases:
different
A,
phases
B,
A,
C.
B, C.
Now,
Now,
what is my degrees of
what is my
freedom at
degrees of
this triple
freedom
point?
at this triple point?
Right? Suppose there is a
Right?
single
Suppose there is a
component.
single component.
If you take
If you
example
take
as water, then it
example
is
as
a single
water, then it is a
component, right?
single component, right?
Everywhere we will find
Everywhere
H2O,
you will
but
find
only
H2O,
you
but only you
find the difference is
find
in
the
difference
difference
in
is the
phases. You
difference in
will find
phases. You will find
liquid here,
liquid here,
you will find
you will
gases here,
find
you will
gases here,
find
you will find like
sorry, you will find
solid.
solid
You
here,
will find
you will
solid
find
here,
liquid
you
here,
will
you will
find
find
liquid here,
gases
and you
here,
will find gases here.
right? That's all.
Right? That's all.
Now,
Now,
solid, liquid,
solid,
gas.
liquid, gas.
Now, what is the
Now, what is
invariant degrees
the
of
invariant? Sorry, what is the degrees of freedom at this point?
So
Right.
number of
So
components,
number of components, 1.
we have fixed
We
the
have
pressure
fixed the pressure
and temperature, right?
and
There are two
temperature, right?
components,
There are
pressure
two
and
components,
temperature.
pressure and
So there
temperature.
are two.
Okay, so there are two.
We didn't fix
We
anything.
didn't fix anything. Okay,
So
so
components one.
components, 1.
How many number of
How
phases?
many number of
One,
phases?
two, three.
One,
Which are in
two, three,
equilibrium
which
at
are
this
in
point.
equilibrium at this point, right?
All three phases are
All
touching
three
this
phases
point.
are touching this point.
So number of
So
phases three
number of phases,
plus
3
two.
plus 2.
One plus two,
1
three.
plus 2,
This
3.
one gets
This
cancelled.
one
So
gets
number of
cancelled.
degrees
So
of
number
freedom
of
equals
degrees
to
of freedom equals to
zero. And
0.
if the number of
And if
degrees
the
of
number
freedom
of
equals
degrees
to
of freedom
zero,
equals to
we
0,
call it
we call it
as
as
a
a
invariance point.
invariance point.
Right?
right?
What do you mean by
What do you
invariance
mean
point?
by invariance
Invariance
point?
point,
Invariance
it
point,
is fixed.
it is fixed.
It does not change
It
with
does
any
not
of these
change with any
parameters.
of these
Even if you
parameters. Even
change
if you
pressure,
tell change
temperature,
pressure,
no, it
temperature,
does not
no,
matter.
it does not
It is
matter.
fixed there.
It is fixed there.
So there is no degrees
So
of
there is no degrees of freedom
available for it,
available for it,
right? So it is
right?
fixed
So it
for
is
the system.
fixed for the system.
Now, that is
Now,
all about
that is all
the Gibbs
about
phase rule.
the Gibbs phase
So
rule. So
now coming to
now
the next
coming
one, the
to the next
clashes
one, the
claptronic
clashes
question.
claptronic question. Okay. So
What do you mean by
what
clashes
do you mean by
claptronic
clashes
question? So
claptronic question? Clashes
claptronic question will tell
claptronic
us
question will
about
tell us
the
about
equilibrium
the
temperature.
equilibrium temperature or the equilibrium pressure.
What happens if
What
you apply,
happens if you apply
change the
if we
pressure
change the
on
pressure
any
on
transformation?
any transformation? If
Suppose
some
a transformation
suppose a
reaction is happening.
transformation reaction is happening,
What happens if you
so
change the
what happens
pressure?
if we change
What
the
happens if
pressure?
you change the
What happens if
temperature?
we change the
So
temperature? So
it will tell you how
it will tell you how it will going to
now.
change. Now,
Suppose if I have a
suppose if I
system,
have a
in a system I
system, and
have
in a
two
system
phases
I have
P1
two phases
and P2,
P1 and
and
P2,
P1
and
has
P1
free
has
energy G
free
alpha,
energy G
and P2
alpha,
has free
B2
energy
has
G
free
beta.
energy G
Now,
beta. Now,
we know the
now
differential
we know the
equation, right?
differential equation,
Famous
right? The
differential
famous
equation for
differential
free energy.
equation for free energy.
dg
dg equals to
equals to
vdp
minus
minus
sdt,
sdt,
right?
right?
So
So I hope
I have derived this
I have
equation
derived this
many times in
equation many
previous
times
sessions,
in
so
previous
I will
sessions,
not
so I will not
derive this again.
derive
If
this
you want
again.
to know, you
If you
can
want
just
to know,
go
you
back
can
to those
just go
sessions.
back to those sessions.
So let me
So
write it for
let me
G
write it for G
alpha phase, then it
alpha
will be
phase, then it will be
dg alpha,
dg alpha,
volume of
volume of
alpha,
alpha,
change in
change in
pressure,
pressure
minus
minus
entropy
entropy
of
of
alpha,
alpha,
change in
change in
temperature.
temperature.
Let me write it for
Let me
beta,
write it for beta,
v beta
v beta,
dp minus
dp minus
s beta
s beta
dt,
dt,
right? So
right?
at
So
equilibrium,
at
this is
equilibrium, this
this
is
one. Now
yes,
what
one
happens
now.
at
What
equilibrium?
happens at equilibrium?
If two phases are
If
at
two phases are
equilibrium,
at equilibrium,
then their free
then
energies
their
must
free
be
energies must be
equal, right?
equal,
G
right?
alpha
So
equals
P
to
alpha equals to
G beta.
C beta.
Now
Right?
what I'm
Now
going to do?
what
I'm
I'm
going
going
to
to do? I am
differentiate
going
on
to
both sides.
differentiate on both sides. So
Differentiate on both sides.
differentiate on both
dg
sides. It will
alpha
be dg alpha
equals to dg beta.
to dg beta.
This
Right?
is one.
This
This
is
is
one.
two.
This is two.
Now from
Now
three,
from three,
one equals to two.
one equals to
So
two. So
v alpha
V
dp
alpha dp
minus s
minus
alpha
S
dt
alpha dt
will be equals to
will be equals to
v beta
V
dp
beta dp
minus
minus
s beta
S beta
dt.
dt. Right?
Subtracting.
Subtracting.
Now suppose
Now suppose
alpha goes there,
alpha
then
goes there, then
v
V
beta minus v
beta
alpha
minus V alpha
dp
dp
will be equals
will
to
be equals to
s beta comes here.
S beta comes here.
S beta
So S beta
minus s
minus
alpha
S alpha
dt.
dt.
Let me write it again.
Let me write it again.
V beta
V
minus
beta
v
minus
alpha
V alpha
dp
dp
is
is equal to
equal to
S
s beta
beta
minus s
minus
alpha
S alpha
dt.
dt.
V beta minus v
V
alpha
beta
is
minus V
delta
alpha
v.
is delta V.
Delta v change in
Delta V
volume
change in volume
equals
equals
to
to into times change
differential
in
of pressure
differential of pressure
into
into
entropy
change in
times
entropy
differential of
times
temperature.
differential of temperature.
What I'm going to do
What
is
I'm going to do is
dp by dt
dp by dt
equals to
equals to
delta s by
delta S by
delta,
delta V.
right? Now
Right? Now,
again from 3,
again from 3,
delta g
delta
of
G of
beta
beta
minus
minus
alpha
alpha
will
will
be
be
equals
equals
to
to
g
G
beta
beta
minus g
minus
alpha,
G alpha.
right?
Right?
So at
So
equilibrium,
at
delta
equilibrium,
g beta
delta G
minus
beta
alpha
minus
will be
alpha
equals to
will be equals to
delta h
delta
change in
H
enthalpy
change in enthalpy
minus
minus
temperature times
temperature times
change in entropy of
change in
the
entropy of the
transformation reaction.
transformation reaction.
So at
So
equilibrium,
at
this will tends
equilibrium,
to
this will
0,
tends to 0,
then
then
delta change in
delta
entropy
change in entropy
of the reaction will
of
be
the
equals
reaction will be equals to
enthalpy,
enthalpy change in enthalpy of the
divided
reaction
by
divided by
temperature.
temperature.
Now
Now what I'm going to do is I'm going to substitute this here.
this will turn
So
out to
this
be
will turn out to be
dp by
dp
dt
by
equals
dt
to
will be equals to
dp by dt
dp by dt will be equals
delta
to
s,
delta s,
that is
that
delta
is
h
delta h
beta minus
beta
alpha
minus
by
alpha
t
by t
times delta
times
v,
delta v.
right? So
Right? So
this is my
this is my
Clausius Clapeyron
Clausius
equation.
Clapeyron equation.
We can even
Right?
simplify
We can
this.
even simplify
For
this.
example,
For example,
let's say
let's say
liquid
liquid
it's
is
transforming
transforming
to
to
gas.
gas.
Now if we increase the
Now, if we
temperature,
increase the
what will,
temperature,
now if we
what will
increase the
now if
pressure,
we increase the
what will
pressure,
happen,
what will happen?
right?
Right?
So
So
we know
we
volume of
we know
liquid
volume of
is
liquid is
very much larger when
very much
compared to
larger when
volume of
compared
gas.
to volume of gas.
We all know that.
We all know that, right?
We have been studying
We
this
have been
from like
studying this from
11th,
like
8th
11th, 8th
standard.
standard.
So
So
VL minus
VL
VG
minus
will be
VG will
approximately
be
equals to,
approximately equals to,
ah, sorry,
ah,
I made
sorry,
a mistake.
I made a mistake.
It's
It's
VG is
VG
much
is
greater than
much
VL
greater than VL
because
because
liquid is a
liquid
condensed
is a
space,
condensed
but
space, but
gaseous is not,
gaseous is not,
right?
right?
So density of
So
liquid is
density of liquid
larger
is
when compared to
larger when
density
compared
of
to
gas.
density of
So
gas.
VL minus
So
VG
VL
can be
minus VG
approximately
can be
equals to,
approximately
or
equals
VG
to,
minus VL
or
can be
VG minus VL can be
approximately equals to
approximately equals
minus
to
VG,
minus
or
VG,
it depends
or it
on how you
depends
write it.
on how you write it, right?
So
So
VG minus
VG
VL
minus
is
VL
approximately
is
equals to
approximately equals to
VG.
VG.
Now,
Now,
on
on
substituting that term
substituting
here,
that term here,
it will be
it
dP
will be dP
by dt
by dt
equals
equals
to
to
delta H
delta H
divided by
divided by
T
T
times V
times V
volume of glass,
volume of glass,
right? Now,
right? Now,
we know
we
delta
know
H
delta H
enthalpy equals to,
enthalpy equals to,
we are
if
talking about
we are
molar
talking about
enthalpy,
molar
then N,
enthalpy, then N,
it is a change,
it is a
right?
change,
Delta G,
right? Delta G,
gaseous minus liquid.
gaseous minus liquid,
So it should
right?
be
So it should be
Cp
Cp
of gaseous
of
minus
gaseous
Cp
minus
of
Cp
liquid
of liquid
dt, right?
dt,
Now,
right? Now,
let's suppose
let's suppose
Cp is only a
Cp
function
is
of,
only a function of,
Cp is only
Cp is
as a
only
function of
as a
A
function
plus
of A
Bt,
plus
just for
Bt,
simplicity.
just for
There is
simplicity.
other equation,
There is other
like
equation,
C
right?
by
There is
T,
C by
and
T,
this terms goes
and
on,
this terms
right?
goes on,
So we are
right?
not going
So we are
to
not going to
worry about
worry
the
about
other terms.
the other terms.
For simplicity,
For simplicity,
we are going to
we are going to
we are only,
we
only
are
going to
only
consider
going to
Cp
consider
equals to
Cp
A
equals to
plus Bt,
A plus Bt,
right? Now,
right? Now,
Cp gaseous minus
Cp
Cp
gaseous
liquid
minus
will be
Cp
again
liquid will be
equals
again
to some
will be
constant
equals to
times
some
that
constant
will be
times
happen.
that
So
will be
delta
happen. So
H
delta H
GL will be equals
GL
to
will be equals
N
to
times
N
A
times
plus
A plus
Bt
Bt
times dt. And
times
for
Bt.
example,
And for
n equals to
example,
1,
N equals to 1,
it's n equal,
it's
n equals to 1.
N equals to 1.
Then
Then
dP
dP
equals to,
equals to, now,
yeah,
yeah.
so
So
dP will be equals
dP
to
will be equals to
T,
T.
no, it's
No,
a change,
it's
right?
a
It's not
change, right?
dH,
It's
it's
not
delta
dH,
H.
it's delta H. So
It shouldn't be
it
coming like
shouldn't be coming like dt
because it's
because
in differential
it's
form.
in
It's
differential
not
form.
differential
It's
form,
not
it is
differential form,
integrated.
it is
So
integrated.
it is
So
difference
it
form.
is difference
So
form.
let's say delta
So
H
let's say
equals to
delta H equals to
A plus Bt,
A plus bt,
right? So
right? So
yeah,
yeah,
let's say n equals
let's
to
say
1,
n equals to 1,
then
then
when dH
when dh, sorry,
equals to
dh equals to
ncPT,
ncp dt.
this is the relation,
This is the relation,
right? So
right?
from
So
this we
from
came to
this,
this.
we came to this.
Okay.
Okay.
Now,
Now,
uh,
uh,
so if we assume
so if
Cp
we
equals
assume
to A
Cp
plus
equals to
Bt,
A
then
plus
delta
Bt,
H will
then
be
delta H
equals to
will be equals
AT
to
plus
AT
Bt
plus
square by,
Bt square by 2.
let's say, after
Let's say
doing
after
everything
doing
calculation, we
everything
arrived at
calculation, we
AT
arrived at
plus Bt square
80
by
plus
2.
Bt square by 2.
That
Now,
is about that.
that is about that.
This V
This
can
V
be
can
brought to this
be
side
brought
and
to
dt
this
will
side
be
and dt will
brought to
be
that
can be
side.
brought
So
to that side. So
dp equals to, now
dp
what is
equals to,
delta
now
H?
what is
Delta
delta
H
H?
is
Delta
my
H is
AT
my
plus
80 plus
Bt square
bt
by
square
2
by 2
divided by T
divided by t
times dt.
times
Now what
dt.
is
Now
dp?
what is
Which is
dp? Which
Vg.
is
So what
vg.
is V?
Now
We
what
know
is v? We know
ideal gas law.
ideal gas law.
PV equals to
pv equals to
RT
rt
for 1 mole.
for one
And what
mole.
is V?
Then what
V
is v?
equals to
V equals to
RT by
rt by p.
substituting that here,
Substituting that
that
here,
will turn out to
that
be
will turn out to
P
be
by
rt
P
by
times
p times
dP
dp
equals to
equals to
AT. Now
at. Now
this T
this
gets
t
cancelled.
gets
So what we
cancelled.
have
So
is
what we
A
have is
plus
a
BT,
plus bt
right?
right?
by 2
By 2
into
into
dt.
dt.
Now we
Now
have other t.
we have other
Now
t
again
here. Now again,
we
we
uh,
uh,
put this term
put
to
this term.
here.
So
We can
here
convert
we
this term
can
to
vote
here.
this
Then
term
it
to
will turn
here.
out
Then
to
it
be
will turn out to be,
so.
so
Keep every constants
keep
here.
every
Then
constants
this
here.
will be
Then
equals
this
to
will be equals
dp
to
by p
dp by p
r
r
times
times
a by t
a by
plus
t
b
plus
by 2
b by 2
integral of
integral of
dt.
dt.
Now let me have one
Now
more
let me
slide.
have one more slide. Sorry.
This was our
This
equation.
was our
Let me write it
equation.
again.
Let me write it again.
dp by p
dp by
which is
p,
equals to
which is equals to
r times
r
a
times
by t
a by t
plus
plus
b by
b
2
by 2
integral of
integral of
dt.
dt.
Now
Now
integrating both sides,
integrating both
the
sides,
constant comes
the
out.
constant comes out.
It will be
It will be
ln p equals
ln
to
p equals to
r.
r.
What is integral of
What
1
is
by x
integral of 1 by
dx?
x
This will be ln
dx,
x.
which is
So
ln x. So
ln t
ln
a
t a
plus
plus
bt
bt
b by 2,
b by 2,
right,
right,
plus c.
plus c.
So this
So
is my equation.
this is my equation.
Now if you want
Now, if
to
you want to
write everything in
write
terms of
everything in terms of
exponential, then
exponential,
it can
then
be
it
written as
can be
p
written
equals
as
to
p equals
e
to
power
e power
ra
ra
times
times
e power
e power
ln
ln
t
t
plus
plus,
sorry
sorry,
times
times
e power
e power
bt by 2
bt by 2
times e power c.
times e power
Now
c.
if I take
Now, if I
constants
take
in one swoop,
constants in one swoop,
so
so
let's say
let's
r
say
a
r
c
a
equals to
c equals
k
to k
e power k
e power k
times and e
times
power ln
and
t
e power ln
which is
et,
equals to
which
again
is equals
t
to again t
times e
times
power
e power
bt by 2.
bt by 2.
So p will be
So
equals
p
to
will be equals to
e power k,
e power k,
or I can take e
or I
power
can
k as
take e power
constant,
k as
e power
constant,
k
e power k
as d,
as d,
or I can take it as
or I
l.
can take it as l, right?
Then
Then
l
l
times
times
t
t
into e power
into e power
bt by 2,
bt by 2,
right?
right?
Now
Now,
question can be framed in
question can
this.
be framed
For
in this way.
example,
For
if
example,
a
if
transformation
a
is happening
transformation is
at
happening
t1,
at t1,
right,
right?
then you have an
Then you
equilibrium
have an
temperature
equilibrium
t1.
temperature
Now what
T1.
happens if
Now,
we
what
change
happens
the
if we change the
transformation pressure to
transformation pressure
T2?
to T2?
Then your equilibrium
Then your
temperature will be
equilibrium temperature will
T2.
be
So
T2. So,
if I put this
if
here,
I put this here,
then
then
I can just
I can just
divide both sides,
divide
right?
both sides,
So
right? So,
L
L
T1 cross
T1
E
cross
B
E
T1 by
B
2,
T1 by 2,
L
L
T2 times
T2
E
times
B
E
T2 by
B
2.
T2 by 2.
T L L
T
gets
L
cancelled.
L gets
So
cancelled.
if you
So,
substitute
if you substitute
the pressures,
the
we will
pressures,
find
you will
any of the
find
term.
any
Like
of the
if
term. Like
we
if
ask
we ask
in questions, they will be
in questions,
framing
they will be
like,
framing
for
like,
example, the
for example,
equilibrium
the
for
equilibrium
pressure
for
P1,
pressure
the
P1,
equilibrium
the
temperature is
equilibrium
V1.
temperature is
Then
V1.
for
Then
pressure
for
P2,
pressure
what will be my
P2, what will
equilibrium
be my
temperature?
equilibrium
So
temperature? So
questions can ask
questions can
that
ask
way.
it in that way.
Now,
No,
so
so
that's all for our
that's all for our
basic thermodynamics,
basic thermodynamics,
right? So
right?
now
So
coming to
now
phase
coming
equilibrium
to phase
and the phase
equilibrium
diagrams.
and the phase
Now,
diagrams.
last class
Now,
we
in
also
last class
derived
we also derived
how the
how
composition
the
will change with
composition will
respect to
change with respect
no how the
to,
free
no,
energy will
how the
change
free
with
energy
respect
will
to
change with respect
composition,
to
right?
composition,
Now
right?
if suppose
Now,
if you
if
have two
suppose if
phases,
you have two phases,
then
then
the final
the
phase
final
after mixing,
phase
the
after
final free
mixing, the
energy
final free energy
will be
will
G2
be
will be equals
G2
to
will be equals to
initial free energy
initial free energy
of alpha
of alpha
plus initial
plus
free energy
initial free
of
energy
beta
of
which will be Z
beta, which
total
will be Z total
plus
plus
XA ln XA
XA ln XA
plus
plus
XB
XB
ln XP.
ln
Now
XP.
this is
Now,
for
this is
ideal
for
solutions.
ideal
Now
solutions.
what
Now,
happens for
what
regular
happens
solutions?
for
For
regular
regular
solutions?
solutions
For
we will
regular
have an
solutions, you
enthalpy
will
term,
have an enthalpy term,
so
right? So
that will be equals
that
to
will be equals to
XA
XA
XP.
XP.
Now
Now,
what about
what about
G final
G
of
final
alpha?
of alpha? right? So G1 initial. See,
See,
you
you
can
can
write
write
this
this
term
term
into
into
components,
components,
right?
right?
So
So
for
for
example,
example,
if
if
you
you
just
just
multiply
multiply
this
this
guy
guy
with
with
XA plus XP, we
XA
know
plus
XA
XP,
plus
we
XP
know
equals
XA
to
plus
1.
XP equals to
So
1, right? So
if I
if I
multiply
multiply
XA
XA
XP times
XP times
XA plus
XA plus
XP, then
XP,
this will be
then
equals
this
to
will be equals to
XA square
XA
plus
square
XB
XP
plus
plus
XB
X
square
B square
XA. Now you can
XA.
take
Now you
any
can
one
take
common,
any one
right?
common,
So
right? So
if I for this
if
one,
I for this
if I
one,
take
if I take
XA as a common,
XA
right?
as
I
a
didn't
common,
mention,
right? I
so
didn't
XA
mention XA
XB, because
XP
G1 is a molar
because
of
G1 is a
free energy,
molar
right?
with free
So
energy,
that's
right?
why
So
mole
that's
fraction.
why mole fraction.
Yeah.
Yeah.
So
So
G final alpha
G
will be
final
equals
alpha
to
will be equals to
G1 alpha
G1 alpha
times omega
times
function.
omega function.
I want to take
I want to take uh,
XA as a common,
XA
right?
as a
So
common, right?
this will be
Then
equals to
this will be
1
equals to
minus
1
XA
minus
square,
XA square
because XB square
because
can be
XB
written
square
as
can be
1 minus
written
XA
as
square,
1 minus
right?
XA square,
So
right? So
I will take this
I
term
will take this term
1
1
for alpha.
for alpha.
Now
Now
plus
plus
again XA common,
again XA
it
common,
will turn out to
it will turn out to be
XA.
log XA.
Now
Now
final for beta,
final for beta,
G2 beta,
G2 beta,
right?
right?
For phase 1,
For phase
we
1,
can write just,
can write just
I don't know, I
I
don't need
don't I don't need I
to
don't
write
need to
G2
write
because I have
G2
already
because I have
mentioned,
already mentioned,
right?
right?
G alpha and G
G
beta.
alpha and G beta.
Yeah, I need to mention
Yeah,
like,
I
yeah,
need to
I need
mention
to
like,
mention
yeah,
for
I need
like
to mention
initial,
for like
one is for
initial.
initial.
One is for initial.
This omega
This
function
omega
times 1
function
minus
times 1 minus
xp square
xp
plus
square
log
plus log
xp.
xp.
Now, if you draw
Now, if
the
you
free energy
draw
versus
the free energy
composition for
versus
total
composition
free
for
energy,
total free
if you have
energy,
two
if you
phases which
have
are
two phases which
suppose
are
immiscible,
suppose immiscible,
right?
right?
Then
Then
not immiscible, but
not
it's
immiscible,
completely
yes,
soluble.
completely
So
soluble. Then
this will be my
this will
XA,
be my XA
XB.
or
This is my
XB.
free
This
energy.
is my free energy. So
The curve will look
a
like
curve
this,
will look like this,
right? From this
right?
equation.
From this equation.
Now
Now
let's draw
let's draw
G versus X
G
diagram
versus X
for
diagram for
our
our
T1 temperature
T1 temperature
at melting
at
T2,
melting
T3, and
T2,
T4.
T3,
So
and
we
T4.
have four
So we have
temperatures,
four
right?
temperatures,
No,
right?
five
So no,
temperatures.
five temperatures.
Yeah, slide.
Yeah, first slide.
So
So
at
at
TA,
what
right? First there
TEA,
is
right?
TA,
First there is TEA,
then there
then
is
there
T1,
is T1,
there is
there
TB.
is TB.
Yeah.
Yeah.
Let's first draw
Let's first
for
draw
these guys.
for these guys.
This is my G,
This is my G.
this is my XB.
This is my XB.
Now,
Now,
how many phases do
how
we
many
have?
phases
We
do we
have three
have? We
phases:
have three
alpha,
phases:
beta,
alpha, beta,
liquid.
liquid.
Now we need to
Now
draw
we need to draw
G
a
versus X
GUS
curve,
X
right?
curve,
So
right?
at first
So at first
the liquid is stable,
the liquid is
right?
stable,
So
right? So
at TA only
at
liquid
TA
is touching,
only liquid
right?
is
So
touching,
this is
right?
my
So this is my
oh, this is
oh,
wrong.
this is wrong.
So cannot be
This
right.
cannot be right.
So my
So
liquid
my
will look
liquid
like
will
this,
look like this. So
right? For
right
GL.
for GL.
Now for G
Now for
alpha,
G alpha,
it will look like
it will look like
this.
this.
And what about G beta?
And what about G beta?
G beta will look
G
like
beta
this.
will look like this.
What?
What?
At T melting.
At T melting,
Melting of
T
A.
melting of A.
Right? Now what
Right?
about
Now
at
what
T1?
about at T1?
T1, so
T1, so
his
his
isothermal line.
isothermal
So
line.
T1 will be
So T1
touching
will be touching
alpha place and liquid
alpha
plus
plus and
alpha, then
liquid plus
liquid,
alpha,
total
then
liquid,
liquid,
right?
total liquid,
So
right? So
like
and this
this is my G,
this is my G,
this is
this
my
is
XB,
my
mole
XB,
fraction of the
mole
atoms.
fraction of the atoms.
First,
First,
this is my liquid,
this is my liquid,
right? Now what about
right? Now
my
what about my
G alpha value?
G alpha value?
Right? At first the G
Right? At
alpha is
first, the G
stable,
alpha is stable,
then G alpha will
then
go
G
out.
alpha will go out.
So this is
So this is
my G
my
alpha.
G alpha.
Still the
Still, the
G G beta is not stable, right? So G beta will come close.
That's all.
That's all.
Now,
Now,
if I draw a
if
common
I draw a
tangent
common
touching
tangent
these two
touching
curves,
these two curves,
right?
right?
So
So
here I have
here I
alpha,
have
here I have
alpha,
total
here I
liquid,
have
here
total
I have
liquid, here I
alpha
have
plus liquid.
alpha plus liquid, right?
That's it.
That's
Now
it.
coming to
Now coming to
melting of the
melting of the
melting temperature of the,
the
right? So
right?
which is
So which
TB.
is TB.
Again, here the
Again,
case will be
here
the
the case
same.
will be the same.
At
At
first,
first, the G will be
alpha will be
alpha will be
stable.
stable.
Then we have
Then we
liquid.
have liquid.
Okay,
Okay,
and erase
and
this.
erase this.
Yeah.
Yeah.
Here the
Here,
GB
the
will GB curve will start
GB
from
curve will
here.
start from here,
Right? So
right? So uh,
G beta.
G beta.
This is my G
This is
alpha.
my G
This is
alpha.
my G liquid.
So G liquid.
Again,
When
drawing the common
drawing the
tangent
common tangent
is alpha
is alpha,
plus liquid.
alpha
This
plus
is my
liquid.
liquid.
This is my
This
liquid.
is my
This is
XB.
my XB.
This is my
This is
G.
my
Now,
G. Now,
what is the next
what is the
temperature?
next
Next temperature
temperature?
is my
Next
T2.
temperature is my T2.
So at
So at
T2,
T2,
at
at
eutectic,
eutectic,
at
at
T3.
T3.
This is my
This is my
XB.
XB.
This is my G.
This is my G.
Now at this
Now,
temperature,
at
right?
this temperature,
So
right?
this
So
isomorphous
this
line is
isomorphous
touching,
line is
not
touching,
isomorphous
or
line,
not
it's
isomorphous
isothermal
line,
line.
it's isothermal line,
Is having alpha,
is
liquid
having
plus
alpha,
alpha,
liquid plus alpha,
beta,
liquid plus beta, and beta,
So there are
right? So
like
there are
one, two,
like
three,
one,
four,
two,
five
three, four,
regions,
five regions,
right?
right?
First,
At
we
first,
have
we
alpha,
have alpha,
then we have
then we
liquid,
have liquid,
and
and then you have
then we have beta.
beta.
And because
And because
liquid is
the
at liquid is still stable,
liquid is still stable,
that free energy
that free energy
must be lower.
must be lower.
Let me
Redraw
redraw
this point.
this. That's it.
That's it.
So
So
this is my
this
G
is my
alpha,
G
this is
alpha,
my
this
G
is my
beta,
G
this is
beta,
my
this is my
G liquid.
G
So
liquid.
if I draw
So
common
if I draw
tangent,
common tangent,
it will
then
go
this
like
will
this,
go like this,
and this guy
and
will
this
have a
guy will
common
have a
tangent like
common
this.
tangent like this.
It is
It
this
is
part
this part
became messy.
became messy. So
Yeah.
yeah.
So my common
So my
tangent
common
must
tangent
come like this,
must
and
come
this
like
common
this, and this
tangent must
common
touch here.
tangent must touch here.
Right.
Right?
So
So
this is my alpha,
this is my alpha,
and here
and here
alpha plus liquid.
alpha plus liquid.
Here I have
Here
liquid.
I have liquid.
Here I have
Here
beta
I
plus
have
liquid.
beta plus
Here
liquid,
I have
and
beta.
here I have beta.
That's all.
Right? That's
Now
all. Now,
what will be at
what will
eutectic
be at
temperature?
eutectic
So
temperature?
this is my
So
G.
this is my G.
This is
This is
my
my
XB.
XB.
Mole fraction of
Mole
V.
fraction of V.
How do they look
Now,
like?
how do they look like?
Right. So
Right? So
let's draw it slowly
let's
so
draw it
that you can
slowly so
understand.
that you can understand.
This is my equilibrium
This is my
temperature.
equilibrium temperature.
Let's say this
Let's
T3
say this T3
is my
is
TE
my
and T4
TE
is my
and
T4.
T4 is my T3. Okay?
So that's what we
So that's what we have.
did the notation.
Did the
So
notation. So
this is my
this is my
isothermal line. So at
isothermal line.
first,
So at
again
first,
I have
again,
alpha
I
as a
have
stable
alpha
one.
as a stable one.
What about liquid?
What about liquid?
Liquid will
Liquid
liquid
will
also
come.
will
Liquid also
form.
will form,
And then you have
and then
beta.
you have beta.
Right?
Right? So
This is my G
this is
liquid.
my G liquid,
This is my
and
free
this is
energy
my
of
free
alpha.
energy of alpha,
And this
and
curve
this
is my
curve is
free
my
energy of
free energy of
beta phase.
beta phase.
Right?
Right?
So
So
if I draw a
If
common
I draw a
tangent,
common tangent,
here it is my alpha,
here it is my alpha and here it is my
because
beta. And
three
because
that
the
common tangent
that
is
common
touching
tangent is touching or
three different
three different
vertices, right?
vertices,
You may
right?
call the
You
three
may call the
minimums.
three
Then what
minimums.
happens?
Then what happens?
So because
So
G alpha,
because
G
G
beta,
alpha,
and
G
G
beta, and
liquid
G
has same
liquid
common
has
tangent,
same
so
common
this phase
tangent. So
will have
this phase will have
mixture,
mixture,
alpha plus beta plus
alpha plus
liquid.
beta plus liquid.
So
So
that is what about
that
this.
is what about this.
Okay.
Okay.
Now
Now
finally to the
finally to the
T3. This
T3.
one is
This one
simple
is rather simple
compared to all
when
other
compared to all other
diagrams, right?
diagrams,
Because there
right?
is no
Because
liquid
there is
here
no
that
liquid
is
here
stable.
that is stable.
Yeah, you can see
Yeah, you
liquid
can
has
see
moved
liquid has moved
a
up
lot.
a lot.
This is my
This is my
G liquid.
G
Now
liquid.
I
Now
have my
I have
G
my
alpha
G alpha
and also
and also
my G
my
beta.
G beta.
If I draw a
If I
common
draw a
tangent,
common tangent,
this is my alpha,
this is my
this is my
alpha,
beta,
this is my beta, and this is my
alpha plus beta.
alpha plus beta.
Right, so this is
Right?
a
So this is
G
a
versus X
G versus
composition
X
curves
composition
for
curves
different
for
temperatures
different
for
temperatures for
eutectic phase diagram.
eutectic phase
Now
diagram.
there are
Now,
different types
there are
of
different types of
reactions.
reactions, right?
You people need to
You
know.
people need to know.
First, let's talk
First,
about
let's talk about
eutectoid.
eutectoid.
What happens in
What
eutectoid?
happens in eutectoid?
Eutectoid,
Eutectoid,
a type
a
one
type
solid,
1
that is
solid,
S1,
suppose
will
S1,
transform
will
into
transform
two
into
different types of
two different
solids,
types of
S2
solids, S2
and S3.
and S3.
Now,
Now,
what happens to
what happens
eutectic?
to eutectic?
See, you can
So you
easily
can easily
understand if there is a tick,
understand if there is a
then
tick,
there is a
then
liquid
there is a
involved.
liquid involved there.
If you
Now,
have
if you
toy,
have
then
toy,
there are all
then there are
solids
all solids involved there.
reaction. So
Reaction,
eutectic
right?
will
So
have
eutectic will have
liquid will
liquid
transform
will
into
transform into
two types of
two
solids,
types of solids,
two different types of
two different
solids.
types of solids, right?
That is eutectic.
That is eutectic.
Now what about
Now, what
peritectic?
about peritectic?
Eutectic.
Peritectic, peritectic.
Pattern for my
Pardon for my
spelling mistakes.
spelling
Now,
mistakes. Now,
peritectic will have
peritectic will have
liquid plus
liquid
solid
plus solid
will turn into
will turn
a
into
solid.
a solid
Is our peritectic,
is our peritectic,
right? Now,
right? Now,
that's all.
that's all.
Let's say for
Let's say for
monotectic.
monotectic.
Now,
Now,
what happens
what
in
happens in
monotectic?
monotectic?
You need to
Right?
know.
You need to know.
So these
So
now
these
again
now
these are
again
all
these are
different
all
types of
different types
invariant
of
reactions,
invariant
right?
reactions, right?
So
So
in monotectic,
in
one
monotectic,
liquid
one
phase
liquid phase
will break down
will
into
break down into
one liquid phase,
one liquid phase,
a different
a
liquid phase,
different
and
liquid
a different
phase, and a different
solid phase,
solid phase,
right? So
right? So
these are all
these
different
are
types of
all different
invariant
types of
reactions.
invariant
You
reactions,
can
or you
find
can find
these types of
these
reactions
types of
anywhere
reactions
in your
anywhere in
textbooks,
your
in your
textbooks,
metallurgical
in your
textbooks.
metallurgical textbooks,
So
right?
these are
So
really
these are really
how can I say the
how
basic
can I say
types
the
of
basic types of
diagrams you can
diagrams
find
you can find
in phase
in
transformation book,
phase transformation book,
right? For
right?
the
For
best example
the
is
best example is the
Fe3C diagram,
Fe3C diagram, the
iron carbide
iron
diagram,
carbide diagram,
right?
right?
So carbon
So
weight
carbon
percent will be
weight
starting
percent will
from
be starting
0
from
zero
zero
to
to
6.67,
6.67,
right? From there
right?
you can
From
find
there you
these
can
two,
find
these three
these three
invariant reactions.
invariant
These three
reactions.
invariant
These three
reactions have
invariant
degrees of
reactions have
freedom
degrees of
equals
freedom
to 0,
equals to zero,
right? So
right? So
this is our
this
eutectic
is our eutectic
phase diagram,
phase
because you
diagram
can see
because you
one
can see
invariance
one
here,
invariance here,
right? For example,
right?
if I
For
try
example,
to
if I try
draw
to
the number of
draw
degrees
the
of
number
freedom
of
there,
degrees of freedom
for
there,
here how many
for
phases
example,
do we
here how
have?
many
We
phases
have
do we have? We
liquid,
have liquid,
two solids,
two
right?
solids, right?
How many components?
How many
A and
components?
B.
A and
So
B. So
components is my 2.
components is my two.
How many are my
How
phases?
many are
3.
my phases? Three.
Plus my pressure is
Plus my
constant here,
pressure
so
is
my
constant
only
here. So my
variant
only
variable is
variant
temperature.
variable
So
is
2 plus
temperature.
1
So
3,
2
3
plus
minus
1,
3
3,
equals
3
to
minus 3 equals
0.
to 0.
Okay, this is the invariance
This is
point.
the invariance
Even if
point.
you change
Even if you
any
change
term,
any
it will not
term, it will
change
not
until unless you
change
change the
until unless
pressure.
you change the
If you
pressure. Like if
maintain your
you
pressure as a
maintain your
constant,
pressure as a constant,
and
and
then
then
this invariant points
this
is
invariant
fixed
point
for
is
this
fixed
system.
for this system, eclectic system. Okay.
Now these are all
Now
different
these
types
are
of
all different types of
reactions.
reactions.
Now
Now
you can see
you can see
there is this
there is this
immiscibility of liquids.
immiscibility of
So
liquids,
first
right?
what
So
happens is
first, what
a
happens
liquid
is a
when
liquid
decreases
when
from
decreases from
T1 to T2,
T1 to T2,
what is happening?
what
Liquid
is happening?
transforms to
Liquid
liquid
transforms to
plus
liquid
liquid, and
plus
this
liquid, and
L2
this
has
L2
less
has
melting point.
less melting
So
point, right?
comparing to
So compared to
this one,
this one,
so that's why it
so
will
that's why it will
transform into solid
transform into
first.
solid first.
That's why you will have
That's why you will have
L1 turn
L1
out to be
will turn out to be
L2
L2
plus S1,
plus S1,
right?
right?
So
So
this guy has a
this
higher
gas
melting
has a
point, so
higher
it will
melting point, so
transform.
it will transform.
That's all.
That's all.
Now
Now
that is about
that is
these four
about
invariant
these four
reactions:
invariant reactions:
eclectic,
eclectic,
eutectoid,
eutectoid,
pentectic,
catectic,
pentectoid.
catectoid.
Now there is also a
Oh, there is
pentectoid
also a
reaction.
catectoid reaction.
Again, toid means
Again,
we
toid
are
means we are
involving
involving
solids.
solids. So
Two types of
two types
solids
of
will
solids
transform
will
into
transform into
different types of
a
solid.
different types of solid.
Mix and transform into
Mix and
different types of
transform into
solids.
different types of
So
solids.
there are total
So there
five
are total
types of
five
reactions.
types of reactions.
Okay.
Okay.
Now this is
Now
our
this is our
immiscibility
immiscibility
reaction, right?
reaction, right? So
Let's draw.
let's draw.
Now
Now
this type of
this type of
is also known as
is also known
binodal
as binodal
decomposition.
decomposition.
Why I'm
Why
calling it a
I'm calling
binodal
a
decomposition?
binodal
Because
decomposition?
you
Because
have
you
two
have
different
two
decompositions.
different
If I draw
compositions. If I draw
like
like
isothermal line,
isothermal
you
line,
have
you
this
have
alpha phase
this
will
alpha phase
transform
will
into
transform into
alpha prime
alpha
and alpha
prime
double
and
prime,
alpha double prime,
right? So that's why we call
right?
it
So
as a
that's why we
binodal
call it as a
decomposition. There is
binodal
another type
decomposition.
of
There is another type
decomposition
of
which is
decomposition which is
spinodal decomposition.
spinodal
So
decomposition.
let's not
So
talk about that.
let's not talk
Let's
about
just
that. Let's just
stick with our
stick with
binodal
our
decomposition.
binodal decomposition.
Now,
Now,
if I draw G
if
versus
I
X
draw G
composition
versus
at
X
different
composition at
temperatures,
different temperatures,
right?
right?
I have
I
T1,
have
T2,
T1,
and
T2,
T3.
and
These are my
T3.
three
These are
different
my three
temperatures.
different
Now,
temperatures.
if I
Now,
try to
if
draw
I
my
try
G
to
versus
draw
X
my G versus
composition
X
diagram
composition
for these
diagram
three
for these
temperatures,
three
let's
temperatures,
start.
let's try.
So, yeah,
So, yeah,
at T1,
at T1,
right?
right?
Now,
Now,
let me draw
let me draw
because
because it's
it's
easy to
G versus
understand. G versus
X.
X.
Now, what I'm going to
Now,
do
what
is
I'm going to do
draw G
is
versus
draw
X
G
at
versus
T1,
X at T1,
right? So,
right?
this is my
So,
alpha, then
this is
this
my
will be
alpha,
also
then
my
this will be
alpha
also
plus
my
liquid,
alpha plus
and this
liquid,
is my also
and this is
alpha
my
plus
also alpha
liquid,
plus liquid,
right? So,
right? So,
at T1,
at
liquid
T1,
is
liquid
more
is
stable.
more stable.
Let me draw,
So,
extend this.
extend this. So,
Liquid is more stable.
liquid is more stable.
No,
No,
it is
it is
GL,
GL,
right?
right?
So,
So,
yeah,
yeah,
that is GL.
that is GL.
Now,
Now,
G alpha
G alpha
will be here.
will be here.
HCl and G
Is
alpha.
GL and G alpha. Now,
Now
again,
what I'm going to
now what
assume
I'm
is
going to assume is
alpha will
alpha
transform
will
into
transform
alpha dash
into
plus
alpha
alpha
dash
prime,
plus alpha
and
prime, and
all these
all these
phases have same
phases
crystal
have
structure.
same crystal structure.
That's what I'm
That's what
assuming
I'm
now.
assuming now. Okay,
So this is my
so this is
assumption.
my assumption.
So
So
many
basically,
phase diagrams
many
have
phase
same
diagrams
crystal
have
structure
same
when
crystal
we
structure
have
when
a
we
binodal
have a
decomposition.
binodal decomposition. Okay,
Now
now
this is at T1.
this is
So
at
at
T1.
every temperature
So
you
at
can
every
see
temperature, you
GL
can
is more
see
stable
GL is
than
more stable
G alpha.
than G alpha.
What about at T2?
What about at T2?
This is
Series
G
G
XB.
XB.
Okay.
Okay,
So
so
at T2,
at
first the
T2,
liquid is
first the
stable.
liquid is stable. right? So
Let's draw it like
let's
this.
draw it like this.
T2.
T2, I have
Liquid stable. Then
liquid
what about
stable.
the
Then what
solid?
about the solid?
Solid curve
Solid
will
curve
look like
will
this.
look like this.
Okay.
Okay,
Let me redraw this
let me
again so
redraw
that
this again
I
so
can
that
draw
I
the chemical
can draw the
potentials
chemical
also.
potentials also.
So
So
this is my
this
liquid.
is my liquid.
My
Now
solid will
my
also
solid will also
come like this.
come like this.
No, it
No,
shouldn't.
it
It's
shouldn't. It's
messy. So it shouldn't look
so
like
it
this.
shouldn't look like this.
Right? Let me
Right?
redraw this
Let me
again.
redraw this again.
The solid
The solid
should
should
look like this.
look like
Then
this. Then
this is my liquid,
this
right?
is my
So this
liquid,
is my
right? So this
liquid.
is my
Then the
liquid.
solid
Then the
must
solid
look
must
like
look like
this. So
this.
if I draw a
So if
common
I draw a
tangent here,
common tangent here,
this is the common
this
tangent
is the
for that
common
guy,
tangent for
and this
that
is
guy,
common
and
tangent
this is
for
common
here.
tangent for here.
So my common
So my
tangent
common tangent
touches
touches
these 2 points,
these 2 points, right? So
touches
touches
these 2 points.
these
Okay.
2 points. Okay.
Now
Now
this my
this
face
my
touches here.
face touches here.
So
So
this is my
this is my
alpha.
alpha.
This is my
This is my
alpha again,
alpha again,
and
and
this one
this
is my
one is
alpha
my
plus
alpha
liquid.
plus
This is
liquid,
my
and
liquid,
this is
and
my
this is my
liquid, and
alpha
this is
plus
my
liquid.
alpha plus liquid.
So
So
please
please
try to understand.
try to understand.
I will redraw
I
this
will redraw
plot
this
again.
plot again.
Okay.
So
This tangent touches
this
this one.
tangent touches this one.
Okay, and this is for
Okay, and
T2.
this is for
Now
T2. Now
coming for T3.
coming for T3.
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 This is my G,
This is my G,
and this is my
and this is my
XP.
XB.
Okay.
Okay,
So
so
at T3 you have
at
an
T3 you have an
invisibility when
invisibility
alpha is not
and
stable.
alpha is not stable.
So
Okay, so
this is my
this is my
GL.
GL.
So my alpha
So my
will look
alpha
like this.
will look like this.
This is because of
This
this
is because of
invisibility,
this
this
immiscibility,
upper curvature.
this upper curvature.
Okay.
Okay.
Then if I draw
Then
a
if I
common
draw
tangent,
a common tangent,
this gives my
this
alpha,
gives my
and this will
alpha,
be
and this will be
alpha
my
dash and
alpha
alpha
dash and
prime.
alpha prime.
This will
And
be
this
alpha.
will be my alpha.
Okay.
Okay.
So
So
yeah, and
yeah,
if you want to
and if
draw
I
a
want to
curve
draw
for
curves
G alpha
for
and
G
G
alpha
alpha
and G
dash and
alpha
alpha dash,
dash and alpha
so
dash,
that can be
so that
drawn.
can be drawn. uh, So
It cannot be
it
above
cannot
this
be
one,
above
because
this
if
one,
it is above
because
this
if
one,
it is
then
above
this
this
curve
one,
will be
then
more
this
stable.
curve will be more stable,
So
right?
it is not
So
allowed
it
like
is
that.
not allowed like that.
Suppose
Suppose
this is my G
this is
alpha,
my G
which is
alpha, which
below
is
there.
below there,
Now
right? Now
this is my
this is my
G
G
alpha dash.
alpha dash.
Now what about
Now what about
G alpha double
G
prime?
alpha double
G
prime?
alpha double prime
G alpha double prime will
look like this.
look like this.
So
So
this is my
this is
G
my
alpha double
G
prime.
alpha double prime.
Okay,
Okay,
and this is
and
my
this
G
is my
alpha,
G alpha,
right?
right?
And
And
down they are stable.
down they are
So
stable.
if
So
I draw
if I
common
draw
tangent here,
common
then
tangent
this
here,
is my alpha
then
dash
this is
plus
my
alpha
alpha
double
dash
dash.
plus alpha double dash.
That's it.
That's it.
Now coming
Now,
to the
coming
most
to the most
complex
complex
diagram,
diagram,
right? So
right?
what type
So,
of
what type of
invariants we are seeing
invariants
here
we are
in
seeing
various
here in
points,
various
right?
points,
So
right?
I have one
So, I have one
invariance point
invariance
here,
point here,
right?
right?
So how many phases
So,
do
how
I
many
have?
phases do I have?
One,
One,
two, three,
two, three,
four, five,
4, 5,
right? I have five
right?
phases.
And 5 phases.
How many
How
components?
many components? Two.
Again, here, how many
Again,
phases
here,
are?
how many phases are?
Okay.
Again,
What is this one?
what is
This is
this
my
one? This is
quadratic
my
reaction.
quadratic reaction, right?
Not,
Not,
yeah, this is my
yeah,
quadratic
this is my
reaction,
quadratic reaction,
and
and
this is my
this is my
eutectic reaction.
eutectic reaction.
So these two
So
are my
these two
invariant
are my
points,
invariant
right?
points,
This
right?
one,
This one,
this is point one,
this is point
this is
one,
point
this
two.
is
This is not
point
my
two, and this is
invariant
not
point.
my
This is
invariant
like
point.
three
This
phases
is
are
like three
meeting here,
phases of meeting here. That's all,
right? So
right? So yeah,
let me erase this
let
one.
me erase this one. We don't misunderstand.
So I have
Yeah.
one.
So I have one.
One is my
One is my
quadratic.
quadratic.
Two is my
Two is my
quadratic,
quadratic,
right? So
right? So
okay, okay.
okay.
Then let's
Okay,
draw
then let's
for how
draw
many phases
for
to
how
have.
many
I have
phases to have.
four
I have
phases.
4 phases.
G alpha,
G alpha,
G beta,
G beta,
G gamma,
G gamma,
G liquid.
G
So
liquid. So
this is my
it is my
temperature
temperature
at
at
T1,
T1,
right? So
right? So
G
G
and
and
XP,
XB,
right? So
right? So
at T1,
at
my
T1, my
liquid is
liquid
more stable
is more stable
and all other
and all other
are not,
are not,
right? So
right?
this is my G
So this is my
alpha,
G
G beta,
alpha, G beta,
and this is my
and this is my
G gamma,
G gamma,
this is my
this is
G
my
beta.
G beta.
Okay,
Okay,
okay.
okay.
Then
Then moving on to
T2,
T2,
right? So
right?
what do we have
So
at
what do
T2?
we have at T2?
At
At
T2,
T2,
this is my
this
XB,
is my XB,
this is my free
and this
energy.
is my free energy.
Moving up,
Moving up,
then at T2 at
then
first
at
I have
T2, at first
alpha
I have
phase,
alpha
then I have
phase,
liquid
then
plus
I have
alpha,
liquid plus alpha,
then I have liquid.
then I have liquid, right?
So
So
going there,
going there,
I have alpha
alpha
first,
first,
then
then
I have liquid plus
I have
alpha, right?
liquid plus alpha, right? So
Liquid plus alpha.
liquid plus alpha.
Yeah, I totally have
Yeah, I
liquid here.
totally have liquid
This is
here.
my G
This is
gamma,
my G gamma.
this is my
This is
G
my
beta.
G beta.
G beta,
G
G
beta,
gamma,
G
G
gamma,
alpha,
G alpha,
G liquid.
G liquid.
Now, if I
Now, if
draw
I
a common
draw a
tangent,
common tangent,
this is my
this
alpha,
is my
this is my
alpha,
alpha
this
plus
is my
liquid,
alpha
this
plus
is my
liquid,
liquid.
this is my liquid. Okay.
So now
So now
at
at
T3,
T3,
at T3 now we
at
have
T3 now we have
two different phases,
two
right?
different
So at
phases,
T3
right?
we
So
have,
T3 we have,
sorry, we
oh
have
sorry,
G beta
we
2.
have G beta 2. Okay,
So
okay.
G beta 2
So G
is
beta 2
G
is
beta is
G
also touching
beta
here.
is also
So
touching here. So yeah.
oh, G
Oh,
alpha
G
liquid plus
alpha,
alpha,
liquid plus
beta
alpha, beta
liquid plus
is
beta.
or
So
liquid plus
everyone
beta.
is at
So everyone
equilibrium.
is at equilibrium there. Okay.
This is for
This
example,
is for example,
this is for this
this
guy,
is for this guy,
T2.
T2.
Let's say it is
Let's
3,
say it is 3,
T4,
3,
T5,
T4, T5,
T6.
T6.
Okay.
Okay.
So let's say that is
So
for
let's say that
T2.
is for
Now going
T2.
for
Now
T3.
going for T3.
Sorry, I thought the
Sorry, I
temperature
thought the
was
temperature was
this one.
this one. So
Let's draw this
let's
again.
draw this
XB.
again.
Right.
XB.
So at first
So at first,
I have
I
alpha.
have alpha,
Right. I have alpha.
right? I have alpha.
Then
Then
then I have
then
alpha
I
plus
have
beta
alpha plus
and
beta
liquid plus
and
alpha.
liquid plus alpha. So we are all at
equilibrium, right?
equilibrium, right? So
Okay.
okay.
Then
Then I have
this
this
is
is,
let's
let's
say
say
this
this
is
is
G
G
beta.
beta.
This is my
This is
liquid.
my liquid.
Yeah,
Yeah,
this is my liquid.
this is my
So
liquid.
this one is
So
my
this one
G
is my
alpha,
G alpha,
G beta,
G beta,
and G
and
liquid.
G liquid.
So if I
So
draw a
if I
common
draw a
tangent,
common tangent,
so it touches
so it
here.
touches here.
So
So
this is my
this is
alpha,
my alpha.
and again
And
because three
again,
vertices
because
are
three
touching
vertices are
to a
touching
common
to a
tangent,
common tangent,
all
then
those three are at
all those three are
equilibrium.
at equilibrium.
Alpha, beta,
Alpha,
liquid,
beta,
and
liquid.
here I have
And
liquid
here I have
itself.
liquid itself, right?
Yeah.
Yeah.
So that is for
So that is for
T3.
T3.
Alpha,
Alpha,
this whole
this
is
whole
equilibrium.
is equilibrium,
Then we have liquid.
then we have liquid.
Now,
Now,
again, which one?
again, which one?
The next one
Then the
is
next one is
okay.
okay,
So that is
so that is
yeah.
yeah.
Next one is
Next
T4.
one is
T4 will
T4.
have
T4
alpha,
will
alpha
have
plus
alpha,
beta,
alpha
beta
plus
liquid
beta,
plus
beta,
beta,
liquid
then
plus
liquid.
beta, then liquid, right?
You have this
You have this
G gamma. I
G
forgot to
gamma. I
mention that.
forgot to mention that. Okay. Now,
Right.
at
T4.
T4.
This is my free
This is
energy.
my free
This is
energy. This is
composition.
composition.
Okay.
Okay.
Now,
Now,
first I have alpha,
first we
then
have
alpha
alpha,
plus
then
beta.
alpha plus beta. Okay.
First
At first,
I
I
have alpha,
have alpha,
then I have
then
alpha plus
I have
beta,
alpha plus
then
beta,
beta, and then
then
liquid.
beta, and then plus liquid plus beta.
Then
Then
I have liquid
I
plus
have
beta.
liquid plus beta.
Then I have again
Then
liquid
I have
plus
again
beta.
liquid plus
Then
beta.
beta, then
Then
liquid plus
beta,
beta,
then
right?
liquid
So
plus beta, right? So
liquid.
liquid.
So my common
So my
tangent.
common tangent,
If I draw a common
if I
tangent
draw a
from here
common
to
tangent
here,
from here to
to
here,
this, then
to
again
this,
from
then again from
here to here,
here to here,
right?
right?
This region is my
This
alpha.
region is my alpha.
Let me
Let
again.
me
This
again.
is my
This is my
G
G
gamma.
gamma.
This is my G
This is my
alpha,
G alpha,
G beta,
G beta,
G liquid,
G liquid,
right?
right?
Now
Now
this is my alpha
this is
plus
my alpha
beta.
plus beta.
Let me erase this
Let
part.
me erase this part.
This is my beta.
This is my beta.
This whole region
This
is
whole
liquid,
region is
and this
liquid,
is my
and this is my
beta plus liquid. So
beta
one,
plus liquid.
two,
So
three,
one,
four,
two,
five
three, four,
regions.
five regions.
So one, two,
So
three,
one,
four,
two, three,
five
four,
regions.
five
T4,
regions.
right?
T4, right?
Now
Now
coming to
coming
T5.
to T5.
Yeah, this
Yeah,
diagram
this diagram
gets more
gets more
messy
messy
messier
messier
with more phases you
with
add.
more phases you add. Okay.
Now
Now
this is my G.
this is my G.
Wait,
We'll
redraw this guy.
redraw this guy.
Okay.
Okay.
So
So
how many
how
regions we
many
have to cover?
regions we have to cover?
At T5,
At
1, 2,
T5,
3,
one,
4,
two,
5,
three,
6,
four,
7.
five,
So
six, seven. Oh,
we have to cover for
we
7
have to cover for
regions.
7 regions.
Okay.
Okay.
First we have
First,
alpha.
alpha.
This is my G
This is
alpha.
my G
Again
alpha.
the same
Again,
goes
the
here
same
also.
goes there also.
G beta
G beta
and
and
G liquid.
G liquid.
After that
After that,
I have gamma,
I
right?
have gamma, right? Yeah,
Gamma.
gamma.
Now
Now,
this is my
this is
G
my
liquid.
G liquid.
This is my
This is my
G gamma.
G
Now if
gamma.
I draw
Now, if I draw a
tangent to this guys
tangent to
only.
this guys only, So this is my
alpha
alpha,
plus beta.
alpha plus beta.
Let me erase this one.
Let me erase this one.
Yeah.
Yeah.
So this is my
So this is my one.
this is alpha,
This is
alpha
alpha,
plus beta. And if
alpha
I
plus
draw
beta, and if I
tangent to
draw
these two,
tangent to these two,
so this is my
so this
beta.
is my beta,
This is my beta
this is
plus
my
liquid.
beta plus liquid.
I'll have
I'll
liquid,
have
then liquid plus
liquid, then
gamma,
liquid
then
plus
gamma,
gamma,
right?
then gamma, right? So
These two guys has a
these two
common
guys has a
tangent.
common tangent.
This is my
This is
liquid.
my liquid,
This is my
this
gamma.
is my
This is my
gamma,
liquid
this
plus
is my
gamma.
liquid plus gamma.
Sheesh.
Sheesh.
It is a
It is
temperature
at temperature
T5.
T5.
So
So
these
but
diagrams get
these diagrams get
more.
more.
It's not
This is
complicated,
not
but they look
complicated, but they
complicated if
look
we know
complicated if
how to.
we know
If you
how
know just
to,
how to
if you know just how to
draw and
draw and
have things in mind.
have
As
things
okay,
in
at
mind.
this
As okay,
temperature,
at
at
this
this
temperature,
composition,
at
this
this
phase is stable.
composition, this
Then you
phase is
can just
stable. Then you can just
make diagram
make
yourself.
diagram
It's not
yourself. It's
that
not
much complicated,
that much complicated,
right? So
right?
in
So
actually we don't
in
draw these
actually we don't
diagrams.
draw these
This was
diagrams.
done by
This
our
was done
softwares,
by our
and from the
softwares, and
softwares you
from the
will get
softwares you will get
direct the phase diagram.
direct the phase diagram, right? So
Yeah,
yeah,
this is just for
this is
understanding
just for
purposes, not
understanding
for.
purposes, not for like.
Okay, so
Okay,
one
so
last
one lost
temperature
temperature
isothermal line, that is
isothermal
my
line, that is
T6.
my
Okay, so
T6.
everyone
Okay,
is
so everyone is
in equilibrium with
in
it,
equilibrium with it, right? Oh,
right?
right,
T6.
T6. So this is my
This
G,
is my
this is my
XP,
XP,
right?
right?
First I
Now
have
first I have
alpha.
alpha,
This
this
is
is
my
my
G alpha,
G alpha,
and then I
and
have
then
alpha
I
plus
have
beta.
alpha plus beta. Right? So
Let's say it is a bit
let's say it is
lower.
a bit lower. It's a
Okay,
bit lower. Okay,
this is my
yeah, this is my
G beta,
G beta,
and then
and then
I have my
I
liquid
have my liquid
beta gamma
beta
on
gamma
the same
on the
timeline.
same timeline, right?
So
So
this is my
this is
liquid,
my liquid,
and
and
this is my
this is my
gamma.
gamma.
So if I draw
So if I
common
draw a
tangent,
common tangent,
I have
I
alpha,
have alpha,
and here
and here
alpha
I
plus
have
beta,
alpha plus beta,
and
and
if I draw common
if I
tangent
draw
for
common
these
tangent
three
for
guys,
these three guys,
so
so
this is my
this is
G
my
gamma.
G gamma,
Now this is
or this is
G
my
liquid.
G liquid. Okay,
This is my G liquid.
so G liquid.
So
So
here my beta is
here my
stable,
beta is stable,
right? Yeah, here my
right?
beta
Yeah,
is
here
stable,
my beta is stable,
and here I have
and here I have
liquid, again
liquid,
three vertices
again three vertices
touching, right? So
touching,
three phases
right?
are
So three phases are
equilibrium, liquid
equilibrium,
plus
liquid
beta
plus beta
plus gamma.
plus
So
gamma.
I have gamma.
Here I have gamma.
That's all.
That's all.
Oh,
Oh,
okay then. So we
okay
have
then.
one,
So we have
two, three,
one,
four,
two, three,
five.
four, five.
Right, five
Right, five
areas covered. So
areas
this
covered.
is my
So
liquid,
this is my
beta,
liquid,
gamma,
beta, gamma,
three are
three
at equilibrium,
are at equilibrium,
right?
right?
And then I have gamma
And
here.
then I have gamma here.
That's all.
Yeah, that's all.
Now,
No,
that's all about
that's all
phase
about
diagrams.
the phase diagrams.
Okay, so
Okay, so
coming to the
coming to the
interface elements.
interface apps.
Now, what do
Now,
I mean?
what do I mean?
No,
No,
it's not like
it's
interface,
not
right?
like interface, right?
Okay.
Okay,
Let's
let's.
start a different
I
topic.
start
Now,
a
what
different topic.
happens
Now, what happens
if the temperature
if the
is
temperature
increased?
is
How the
increased? Right? How
solubility
the
changes with
solubility
temperature?
changes with
That
temperature?
was the question,
That
right?
was the question, right?
And
And
so I will derive
so
that.
I will derive that.
Okay, so you
Okay, so you can understand that
much clearly.
much clearly.
So,
So
okay then.
okay then. Now
The solubility is
the
very low
solubility is
such
very
that
low,
my
such
G
that
versus
my G
X curve.
versus X curve.
Suppose this is my
Suppose this is my
XB equals to 1.
XB equals to 1.
So my solubility
So
is
my
very low
solubility is
such
very
that my
low,
G versus
such
X
that my
curve
G
will look
versus
like
X curve
this.
will look like this.
Okay.
Okay.
So
So
this is my other
this is
vertices.
my other vertices.
So if my tangent
So
is
if my
there, then
tangent is
this will
there,
touch
then
at
this will touch at
mu B,
mu B,
chemical potential
chemical
of
potential of
B in
B in
beta. Now what
beta.
is this
Now
point?
what is this point?
This point is
This
my
point is my
free energy
free
of
energy
B
of
in
B in
beta form.
beta form.
Okay, suppose
Okay, suppose
alpha is my
alpha
FCC.
is my FCC.
I'm just taking it for
I'm just
example.
taking it for example.
Beta
Now beta
is my
is my
BCC.
BCC. Okay,
So
so
these two are
these two
two
are
different
two
phases.
different processes.
One is alpha,
One is
one is
alpha,
alpha.
one is
Suppose
alpha.
it
Suppose
has
so
iron.
it has
So
iron.
beta, for
And
example, a
beta, for
different
example, a
phase is
different phase,
BCC.
which is a BCC
Suppose
phase.
you have a
Suppose I have
so there are two
so
different
there are
phases.
two
Now what
different
I'm trying
phases.
to
Now
do
what
is
I'm
I'm
trying to
trying to
do is
mix it.
I'm trying to mix it.
Now
Now
beta is
beta is
able
B
to
is
dissolve
able
in
to
A,
dissolve in A,
but A cannot
but
be dissolved
A
in B,
cannot be dissolved in B.
right? So that
Right.
is
So that
the
is
diagram, the space diagram
the
shows,
space diagram shows.
right?
Right.
Now,
Now,
so here
so here from this
I
guy,
zoomed it out,
I
right? So
zoomed
if
it
I
out, right?
zoom
So
it,
if
it will
I
look
zoom
like
it,
this.
it will look like
So
this. So
here I
here I
confirmed that my
confirm
assumption
that
is
my
that
assumption is that
beta
GB
is
beta is
approximately
approximately
equals to
is equals to
mu b
mu B
beta.
beta.
Okay.
Okay.
Now
Now
again,
again,
what is
what
GB
is GB
alpha?
alpha?
So for
So
example, if
for
B is my
example, if
element,
B is my
suppose if I
element,
take
suppose
B
if
as
I take
iron,
B as iron,
okay. Now
okay.
my
Now
iron
my
exists as
iron
BCC.
exists as
Now
BCC.
what does B
Now what does
alpha means?
B
My
alpha means?
iron is
My iron is
forcefully
forcefully
made.
made.
For example, this is at
For
room
example, this is
temperature
at room
T1.
temperature,
Let's
T1.
say T1 is my
Let's
room
say T1
temperature.
is my room
Just
temperature.
for
Okay, just
assumption.
for assumption.
My beta
My
is iron.
beta is iron.
Okay, so it is
Okay, so it is
BCC. B is my
BCC.
iron.
B
It
is
is in
my iron.
BCC
It is in
resource
BCC
section. Okay,
resource section.
so
Okay,
far so good.
so far so good.
What
Now,
is my
what
GB
is my
alpha? That
GB
means my
alpha? That
iron
means
is
my
in alpha
iron
form.
is in
So it
alpha
is
form. So it is
forcefully made
forcefully
into alpha
made
form, which is
into
not
alpha form,
possible.
which is not possible.
That's why we have higher
That's why
free
we have
energy.
higher free
So
energy.
let's just an
So
assumption.
let's just an
So
assumption.
GB beta
So
means
GB beta means
iron in BCC
iron in
phase,
BCC phase,
right? Now
right?
GB alpha
Now
means
GB
iron
alpha
in
means
FCC
iron in
phase
FCC
at
phase
room temperature,
at room
which is not
temperature,
possible
which
again
is not
because
possible
it has
again.
high free energy.
It has
That's why
high
it
free
has
energy.
very
That's why
high
it has
energy.
very high free energy.
So that's
Right?
all.
So that's
Now
all. Now
GB
GB
beta minus
beta minus
GB alpha.
GB
It
alpha.
is delta
It
GB.
is delta
What is
GB.
this? This
What
is
is
the
this? This is the
transformation. Transformation of
transformation of
beta BCC
beta BCC of
beta BCC into
beta
alpha
BCC
BCC
into alpha
at a given
BCC at
temperature.
a given
Okay,
temperature. Okay,
I will write it
I
again.
will write it again.
Transformation
Transformation
of
of
element B
element B
from
from
BCC
BCC
structure
structure,
BCC structure
BCC structure
to
to
FCC structure.
FCC structure.
Now this is my
Now, this is my
delta G, the
delta
transformation
GB,
of
the
element B
transformation
from
of
BCC
element B
structure
from
to
BCC
FCC
structure
structure.
to FCC
Okay,
structure. Okay,
so far so
okay,
good.
so far so good.
Now
Now,
let me write this.
let me write
What is mu
this.
B
What is mu B
mu
alpha?
B
Mu
beta,
B
right?
beta, right? So
Mu B beta
mu B
will be
beta
equals to
will be equals to
GB
GB
beta
beta
plus
plus
T.
RT.
No,
Now,
I'm talking about
I'm
chemical
talking
potential,
about
right?
chemical potential,
So
right? So
let me erase this
let me
part.
erase this part.
One erasing
Upon erasing
GB beta
GB
plus
beta
there is
plus
this for
there
regular
is this
solution
for
this
regular
term.
solution this term.
Okay,
Oh, okay,
this omega
this
times
omega
1
times
minus
1 minus
xp whole square
xp whole square
plus
plus
RT
RT
ln
ln
xp,
xp,
right?
right? Right.
Okay.
Okay.
Now,
Now,
mu b.
mu b.
Yeah. So
Yeah. So
this will turn out to
this
be
will turn out to be
mu b
mu b
beta chemical
beta
potential
chemical potential
minus
minus
gv
gv
beta
beta
equals to
equals to
omega
omega
1 minus
1 minus
xv square
xv
plus
square plus
rt
rt
ln
ln
xv.
xv.
Now,
Now,
what can I
what can
change
I
here?
change here?
So,
So,
what else can I
what
change?
else can I change?
I can write
I can write
gv
gv
alpha here,
alpha here,
right?
right?
So,
So,
at equilibrium,
at equilibrium,
mu b
mu b
beta will be equals
beta
to
will be equals to
mu b
mu b
alpha,
alpha,
right?
right?
So we can write this.
So we can write
We
this.
can write
We
like
can
this,
write
right?
it like this, right?
So
So
then
then
this will turn out to
this
be
will turn out to be
gb
gb
alpha
alpha
minus
minus
gb
gb
beta
beta
will
will be
equals
equals
to
to
omega 1
omega
minus
1 minus
xp square
xp
plus
square
rt
plus rt
ln
ln
xp.
xp.
What is this?
What is this? This is
Delta gb,
delta gb,
right? Now,
right? Now,
again,
again,
here
here
xb
xb
is
is
very very low,
approximately very, very low,
like
right? Like
less than
less
1.
than 1.
Then
Then
this term
this
can be
term
safely
can
made
be
it to 1,
safely made it to 1,
right? So
right?
that will be equals
So
to
that will be equals to
omega
omega
plus rt
plus
ln
RT ln
xp.
XP.
Now,
Now,
xb will be
XB
equals to
will be equals to
e power
e power
minus
minus
delta gb
delta GB
minus
minus
omega
omega by
rt.
RT.
So this is
So
how
this is
the
how the
composition
composition
changes with respect
changes
to
with respect
the
to
temperature,
the temperature,
right?
right?
So
So
this is how the
this is how
composition
the
variance,
composition variance,
right? So
right? So
let's
so
say if you
let's
write
say
it for
if you
alpha,
write it for alpha,
yeah. For
yeah.
example, if you write
For
it for
example, if
alpha
you write
phase,
it for alpha phase,
if you want to check how
if
the
you want to check how
solubility
the
of alpha
solubility
is
of
changing,
alpha is changing,
okay?
okay?
So this
So
will be
this
again
will
xb
be
square.
again XB
These
square.
things won't
These
change.
things won't change.
Yeah.
Yeah.
So gb alpha,
So
now
GB
we know
alpha, now
mu
we
b
know
alpha
mu B
where
alpha,
at
where
chemical
at
potential
chemical potential,
we change
it will change
these guys also.
these guys also.
Mu b alpha, gb
Mu B
alpha.
alpha,
Now
GB
at
alpha.
chemical
Now
potential
at
we
chemical
know
potential, we know
mu b beta is
mu
equal
B
to
beta is equal
mu b
to
alpha.
mu B
So
alpha. So
this mu b
this mu B
this mu b alpha can be
this mu
written
B
as
alpha can be written
mu b
as
beta,
mu B beta,
right?
right?
So mu b beta
So
we
mu
know
B beta, we know
mu b beta is
mu
equal
B
to
beta is
gb
equal
beta.
to GB beta.
Then this will be
Then
converted
this
to
will be
gb
converted
alpha
to
minus
GB alpha minus
gb beta.
GB beta.
That's all.
That's all. Okay.
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 Maybe
Then.
I made
Maybe I made. Uh,
yeah.
yeah,
That's all.
that's all.
Now this is how
Now
the
this is how
composition
the
changes
composition changes
with temperature,
with
right? The
temperature,
solubility
right? The
changes with
solubility
temperature
changes with
specifically
temperature,
for only this
specifically for
diagram.
only this
If we
diagram.
change the
If we
diagram
change the
again,
diagram
these
again,
whole equations
this
will
whole
change. So
equations will change.
it is only for
So
this
it is
one.
only for this one.
Okay. So
Okay. So
at first our basic
at first
assumption
our
was
basic
we zoom
assumption
it out.
was we zoom it
We
out.
choose
We
that
choose
mu b
that
equals to
mu b equals to
mu b beta is
mu
equals
b
to
beta
to
is
draw a
equals
common
to draw a
tangent.
common tangent. This is my
Common
common tangent,
tangent
and common
touches one
tangent
side.
touches one side.
That
Then
point
that
will be my
point
chemical
will be
potential.
my chemical
That point will give
potential.
me
That
chemical
point will give
potential.
me
So
chemical
chemical potential
potential.
of
So
V
chemical
beta.
potential of V in beta.
Okay.
Okay.
So far so good.
So far so good.
And this point,
And this
this
point,
extremity will be
this
my
extremity will be my
GB beta.
GB
Now what
beta.
did I say?
Now, what did I say?
Because
And
the
because
solubility is
the
very low,
solubility is very low,
this
this gap can be considered negligible, which is GB beta minus mu B beta is approximately equals to zero. This is my first assumption here. From there, we arrive to this, right? And we also notated one transformation, which is GB beta minus GB alpha. So from there, I drawn the chemical potential for B in alpha phase, right? So from there, again, from if two phases are in equilibrium, then any component chemical potential must be same in all the phases. So that we substituted here. So mu B alpha can be written as mu B beta. Now again, we know it's the minus here. Yeah. So mu B beta equals to GB beta. This assumption. So that's why GB beta minus GB alpha. So that is my transformation. So this is how my XB changes with temperature. That is about that. Now coming to the interfaces, interface effect. Now before going to the interface effect, there was an equation where Sir said that everyone should know, right? Where the excess pressure is given as 2 gamma by R, right? Now how do we derive that? How do we arrive to this, right? Now I'm going to derive that. So let's say this is my soap bubble, okay? And what I'm going to do is I'm going to take only this part, a very small part, okay, very tiny part. Then how does this part will look like? In zoom, if we zoom that, so it will look like this, almost flat, but it's not flat, okay. So at extremities we have this tension, the surface tension. If you're talking about liquids, okay, right? So there is this tension that is T acting on both sides. Now, for our sake, let's say it's just a force. Okay, let's not talk about separating tension now. For just simplicity, let's take that is as a force. Now, so this is my theta, this is my theta, right? Then, if this is my t, if again I zoom this part, okay, so that part, if I zoom this part, it will look like this, right? So this is my t, this is my two sides, okay. Now, this is, if this is theta, then this also again will be theta, okay. Now it's just basic angles and triangles. You can do that, or if you want, I can do that also. So let me erase this, and so that it is more understandable, let me use blue one. So if I zoom it out, this part, it will look like this, okay. Now, how do we arrive to this triangle? Again, if I zoom this part, okay? So this is my theta, right? This is my theta, and I have two components here. One is my perpendicular, this component is my tension, this is my horizontal, and this is my vertical. So this is my force F. Now this is 90, this is 90 minus theta, then this will be theta, right? Then again this will be 90 minus theta, again this will be theta, right? Why? Because if I extend this one, so this is how they look like, okay. Now we know how this theta came from. Now this will be my t cos theta, and this downward will be my T sine theta.
And same goes
And
for here.
same goes for here.
So this is my
So
T
this
cos
is my
theta,
T cos theta,
and this downward
and
force
this
is my
downward force
T
is
sine
my
theta.
T sine theta.
This is my T
This
sine
is my
theta.
T sine theta.
Okay.
Okay.
Now
Now
again T sine
again
theta.
T sine theta.
So T
So
cos theta, T
T
cos
cos
theta will
theta, T
cancel
cos
out,
theta will cancel out.
right? So
Right. So
these two will cancel
these
out.
two will
Now I'm
cancel out.
only
Now
remaining
I'm
with
only
2T sine
remaining with
theta.
2T sine theta.
Right. So let's say
Right. So
this
let's
T
say
is
this
F.
T is F.
I'm just
Okay.
taking for
I'm just taking for
force.
force.
Force. Okay.
Force.
So
Okay. So
that will be turned out to
that will be turned out to be
2T
2T
sine theta.
sine
That
theta.
is
That
equals
is
to,
equals to,
now what is
now
that equals
what
to?
is that
That will
equals to?
equals to
That
the
will
excess
equals to
pressure.
the excess pressure.
Pressure
The
difference.
pressure difference.
Pressure difference.
Pressure difference. That
D
is
delta P.
D delta P.
That is
That
acting
is acting
on area
on
A.
area A. If I do
Delta P
delta
times
P
A.
times A,
That is my
that is my
F2. Now
F2,
this is my
or this is my
F1.
F1.
Now when
Now when
so bubble is at
so bubble is
equilibrium,
at equilibrium,
F1
that
must be
F1
equals to
must be equals to
F2.
F2.
So
So
2T sine
2T
theta
sine theta
will be equals to
will be equals to
how much?
how much?
Delta P cross.
Delta P cross A.
Delta P
Delta P
cross A.
cross A.
Now again,
Now again,
so
so
going to that.
going to that.
Now
Now
delta P.
delta
So
P.
we need to know
So
what is
we
that
need to know
area,
what is that
right?
area,
So
right?
first
So
I
first
need to know
I need to know
if this
it
is my
if
cap.
this is my
It just
cap.
looks
It
like cap,
just
right?
looks like cap, right? So
Let's say one
let's say one
differential element.
differential element. Okay.
If this is my
If this
differential
is my
element,
differential element,
now
now
how do we
how do we
calculate total
calculate
area?
the total
So
area, right? So hmm,
right. So
right. So
this is
this is
my
my
slip.
slip.
If this is my
If this
theta,
is my theta,
and
and
this is my d
this is
theta,
my d theta,
and this is my
and this is my
small r.
small
Only
r.
that strip
Only
radius.
that
Now
strip
this is my
radius. Now
capital
this
R.
is my capital R.
Now,
Now,
how do we derive
how
that?
do we derive
Now
that?
what is this
Now,
area?
what is this area?
This
This
guy's
guy's
area
area
equals
equals
to the
to
circumference.
the
That is 2
circumference
pi
2
r
pi r
times
times
this length,
this length,
right? Now
right?
what is that strip?
Now, what is that
Strip
strip?
is
Strip
suppose
is
dl.
suppose dl.
Now we know
Now we know
dl
dl
times dl.
times
Now we
dl.
know dl
Now we know
equals to
dl equals to
arc length
arc length
equals to
equals
d
to
theta by
d theta by
sorry d
sorry
theta
d theta
equals to
equals to
times radius.
times radius.
So now
So
substituting
now
there.
substituting
So
there,
a equals
so
to
a equals
2
to
pi
2
r
pi r
times
times
r theta
r theta
r d theta.
or d theta,
Now
right? Now
let's say this
let's say this
f2
f
f
2
sine
f
theta.
sine theta.
I'm still taking
I'm
these
still
as
taking
f.
this as f. Okay.
At last I will
At
change
last I will change. So
2 f sine
2 f
theta
sine theta
equals to
equals
what is
to
my delta
what
p.
is my delta p?
Now that is my
Now
change in
that is my
pressure,
change in
the excess
pressure,
pressure.
the excess pressure.
Now what is
Okay.
my a?
Now what is my
A
a?
is my
A
2
is
pi
my
r
2 pi r
cross
cross
r d
r
theta.
d theta.
So
So
this is my f.
this is my
Now
f.
what is my
Now what is
surface
my
tension?
surface
Surface
tension?
tension is
Surface
force per
tension is
unit length.
force per unit length.
Right? You can see
Right? You
that
can
this is
see that
surface
this is
tension
the surface
for
tension for
on any surface
on
of a
any
liquid.
surface of a
Let's take
liquid.
this
So if it's
with
taking
surface
with
film,
the
and
surface
this is
film,
my
and this is my
suppose this is my stick,
suppose this is
and
my
I'm
stick,
applying
and if I'm
force,
applying force,
right? Force on this
right,
direction.
force on
That is
this
my surface
direction, this
tension
my
will be
surface
equals to
tension will be
force per
equals to force
the
per
unit length
the unit
that
length
we are acting on.
that we are acting on. Okay.
So
So
F by L. Now
F
this
by
L
L. Now
is
this L
equals to
is equals to
this,
this,
the whole
the
circumference,
whole
the whole
circumference, the
circumference of
whole
that cap.
circumference of the cap.
Okay, so
Okay.
2
So
times
2 times
F
F
divided by 2 pi
divided by
r
2 pi r
times sine theta
times sine theta
equals to delta
equals
pi
to delta pi
r d
r
theta.
d theta.
Okay,
Okay.
so
So
now if I do the
now if
difference
I do the
integration
difference
part,
integration
okay,
part,
so this
okay,
will turn out
so
to d
this will
theta
turn
will
out
be
to d theta
directly
will be
equal to
directly
theta.
turn out to
So
theta.
2 times
So 2
surface
times the
tension,
surface
times if
tension
I am talking
times if
about the
I'm
small
talking about
angles,
the
then
small
sine
angles,
theta will
then
be
sine
equals
theta
to
will be equals to
theta, right?
theta,
So
right?
this is my
So
theta
this is my theta
times delta
times
p.
delta
Now
p.
upon
Now upon
integrating, the
integrating,
d
the
theta will be
d theta
turning
will
into
be
theta.
turning into theta.
Let
Let
me
me
draw
draw a line here.
on integrating
On
this, d
integrating
theta
this,
will be
d
turning into
theta will be
theta.
turning into
So
theta. So
this theta
this
theta will get
theta
cancelled.
will get
So
cancelled.
2t
2t
by r
by r
equals to
equals to
delta p,
delta p.
right? So this is how
Right. So this is how
we derive that.
we derive that.
This is my excess
Now this
pressure.
is my
Now
excess
what is my
pressure.
change
Now
in
what is
free
my
energy
change
due
in
to the
free
excess
energy due to
pressure
the
will
excess
be equals
pressure
to
will be
delta
equals
p
to
cross
delta p
v,
cross v.
right? So v is
Right. So
the
v is
volume
the
of that
volume of the
bubble. Okay,
bubble. Okay.
delta g
Now delta
will
G
be equals to
will be
2.
equals
If
to
you are
2.
talking about
If you're
solids,
talking
then the
about
surface
solids, then
tension
the
will be
surface
changed
tension
into
will
surface
change
energy.
into surface
Okay, so
energy.
2
Okay.
gamma
So 2 gamma
r
by r
into
into
total volume.
total volume.
Now this is change in
Now
free
this is
energy
change in
due
free
to
energy due
surface, due
to
to the
surface,
interface,
due to the interface.
right?
Right.
Yeah.
Yeah.
Now
Now
that is how
that is
we
how
arrive
we
to
arrive
that.
to that.
Okay.
Okay.
Now coming to
Now coming to
the Fick's law,
the fixed
right?
law,
So
right?
so far we have
So
discussed
far
about
we
the
have discussed
thermodynamics
about the
part. So
thermodynamics part.
thermodynamics
So
will tells us
thermodynamics will tell us
whether a
whether
reaction will
a
happen
reaction
or
will
not.
happen
That's
or
all.
not. That's
It
all.
doesn't tell
It
you
doesn't tell
anything
you
more
anything
about anything
more
else.
about anything
It
else.
tells you
It
whether
tells you
the
whether
reaction
that
is feasible
reaction is
or not.
feasible or
That's all.
not.
That
That's
is
all.
about
That is
thermodynamics.
about
Now if
thermodynamics. Now, if
you want to know
you want to
how
know
fast a
how
reaction is
fast a
happening,
reaction is
then you need to know
happening,
the
then you
kinetics
need to
part.
know the
Now
kinetics part.
kinetics part
Now, the
depends
kinetics
upon
part depends upon
the moving of
the
species,
moving of
right?
species,
So
right?
that
So
depends upon the
that
diffusion.
depends upon the diffusion.
The next
So
part we
the
are going
next
to do
part we are
is the
going to
diffusion.
do
How
is the
fast the
diffusion.
atoms
How
are
fast the
moving
atoms are
inside a
moving inside a
crystal or inside a
crystal or
material.
inside a
So
material, right? So
not a
that
crystal.
not a
So
crystal.
we are talking
So
about
we are talking
the
about the
material.
material,
So
right? So
yeah, for example,
yeah, for
if I
example, if
bond
I
two
bond
different types of
two different
materials,
types of
A and B,
materials, A and
now
B,
it has
now it has
and due to chemical
and
potential
due to
difference,
chemical
it
potential
will
difference, it will
change from here to here,
change from here to
and
here,
B will come
and B
here to
will
here,
come here to
right?
here,
So
right? So
that's the difference.
there's
Now
a
we
difference.
need to
Now we
understand
need
what
to
is the
understand
diffusion.
what is the diffusion.
Diffusion is nothing but the
Diffusion is
movement
nothing
of
but the movement of
atoms.
atoms.
Uh,
Now,
the
uh,
movement of atoms
the
here
movement
is
of
taken
atoms
as a
here is
random
taken
law.
as a random law,
Okay,
right? Okay.
so
So
the flux
the
will
flux
be given
will
as
be given as
number of moles.
number of
For
moles.
now, for
For
these
now,
sessions, I'm
for
going
these
to only
sessions, I'm
take
going to only take
the moles concept.
the
Okay,
moles
so
concept.
number of
Okay,
moles
so the number of moles
per centimeter
per
square
centimeter
per
square
second.
per second,
Right. So
right? So
this is my
this
flux
is my flux
now.
now.
Okay.
Okay,
So
so
how do we define it?
how do you define it?
Flux. Let's say
Flux. Let's say I have one.
now how do we derive
Now,
that
how do we
formula?
derive that formula?
So
So,
Sir had
Sir
written the
had
basic
written the basic
flux equation, right?
flux
J
equation,
equals to
right? J
minus d
equals to minus d
dou c by
dou c by
dou x.
dou x.
Now how do we arrive to
Now,
this
how do we
one?
arrive to this one?
Okay, so that's the
Okay,
question.
so that's the question.
I'm
Now,
going to derive that
I'm going
part.
to derive that part.
Let's say this is my
Let's say this is
atomic
my
plane
atomic plane
A1.
A1.
This is my
This is my
atomic plane
atomic plane
A2. So
A2. Okay,
this is
so this is my
P1 and this is
P1
my
and this is
P2.
my
Now
P2.
atoms are
Now
jumping
atoms are
from here to
jumping
here,
from
and
here
also
to
the
here,
atoms
and
can
also the
jump
atoms
from
can jump
here to here.
from here
Now
to here.
distance
Now
between them
distance
is
between them
delta
is
x.
delta x.
Okay, so there are
Okay,
two
so there are
parallel
two
planes
parallel
that
planes
are facing each
that are
other.
facing each
So
other,
atoms are
right?
jumping
So
from here
atoms are
to there
jumping from
and
here
here
to
to
here
there.
and here to there.
So these two are
So
these
these two
planes.
are these
Okay.
planes. Okay.
Now
Now,
at first,
at first.
let's write about
Let's write
the moment
about
of
the
flux from
movement of flux from
P1 to
P1 to
P2.
P2.
Okay,
Okay.
movement from P1
Movement
to
from
P2.
P1 to P2.
So the flux
So
will
the
be
flux will be
flux will be given
flux will
as
be given as
so if we want to be to
so
the
if we
flux
want to
will
be
be
to the
given
flux will
J1
be given
into
J1 to
J1 to 2,
J1 to 2,
right?
right?
J1 to 2.
J1 to 2.
So this is my
So
flux
this is my
from
flux
plane 1 to
from
plane
plane
2.
1 to plane
Now how
2.
do we write
Now
it?
how do we write
So
it?
for
So
example there is
for
an atom
example, there
here
is an
sitting
atom
here,
here sitting here,
right? So
right?
it
So
will
it
try to
will
jump
try
from
to
here
jump
to
from
here,
here to
right?
here,
So
right?
it can jump
So
from
it can
either
jump
here to
from
here or
either here to
here
here
to
or
there, right?
here to
So
there,
if
right?
I
So
assume it
if
is
I
a
assume
random
it is a
walk,
random walk,
and if I am
and
assuming a
if I am assuming a
three-dimensional
three-dimensional
state,
state,
then it can
then
move
it
either
can
move in this
move either
direction,
move in this
it
direction,
can also move
it
in
can
this
also move
direction,
in this
or it can
direction,
also move
it
in
can
z
also move in
direction.
z
So
direction. So
it can move in
it
three
can
different
move in three
directions, and
different
also it
directions,
can move
and
in
also it can move in
negative directions.
negative
So the
directions. So the
probability to move in
probability
one
to
direction
move in
is
one direction is
1 by 6
1 by 6
times
times
the jump
the
frequency.
jump frequency.
Now, how
Now,
often?
how
So, for
often?
example,
So,
sir
for
has
example, sir has
defined about the saddle
defined
point,
about the
right?
saddle point,
So,
right? So,
if an atom is
if an
here,
atom is here,
and
and
this guy
this guy
wants to jump
wants
from
to jump from
here to here,
here to here,
so
right? So,
there might be number
there
of
might be
jumps, but
number of
all
jumps, but
might
all
not be
might
possible.
not be
So there
possible.
might be
So,
only
there
one
might
jump
be
that
only
is
one jump
possible.
that
So
is possible.
it
So,
tries to
it
go
tries
from here to
to go
here.
from here to
So
here,
that
right? So,
frequency
that
is given as the
frequency is
jump
given as the
frequency,
jump frequency,
right?
right?
Times
Times
the number of
the
atoms
number
per
of
unit
atoms
volume
per
here,
unit volume here,
right? So
right?
the number of
So,
atoms
the
here
number of atoms here
at this point, the
at
number
this
of
point,
atoms
the
per
number
unit
of
volume,
atoms per unit
and that
volume,
will be
and
given
that
as
will be given as
N1,
N1,
right?
right?
Okay.
Okay.
This from
This
J1
is
to
from
2. Now
J1
what
to 2.
happens from
Now, what
J2
happens
to 1?
from J2 to
The
1?
same thing
The
happens.
same thing happens.
Jump frequency
Jump
times
frequency times
N2.
N2.
So for example,
So, for example,
so
so
so for example,
for
J1 to
example,
flux is
J1
greater
to
than
flux
J2
is
1
greater than
flux.
J2
So
1
for
flux.
example,
So, for example,
J1 to flux
J1 to
is greater
flux
than
is greater than
J2 1
J2 1
flux.
flux.
Then
Then
the total flux,
the
the net
total
flux,
flux, the net
J
flux,
net
J net,
will be equals to
will be equals to
1 by 6.
1 by
The jump
6. The
frequency
jump
is same. If you
frequency
assume
is
the
same.
jump
If you assume
frequency
the
is
jump
same
frequency
because
is same, because
we assume the
if
same
we
type of
assume the
structure
same type
here
of
and there,
structure
there
here
is
and
same
there,
type
and
of
there is same type of
atomic potential
atomic
of both
potential
planes,
of both planes,
then that will be equals
then
to
that will be equals
N1
to N1
minus N2.
minus N2.
Now what is my
Now,
N1?
what is my N1?
N1 is number of
N1
atoms
is
per
number
unit
of atoms
volume.
per unit volume,
So
right? So,
no, the
no,
number of atoms
the
per
number
unit
of
area,
atoms per
right?
unit
So
area, right? So,
N equals to
N equals to
number of atoms
number of atoms
per unit
per unit
area
area
on one side,
on one side,
right? On plane
right?
one,
On plane one.
right? Now
Right. Now,
we know
we
C1.
know
What is C1?
C1. What is
It is
C1? It is
concentration
concentration
at
at
plane one,
plane 1,
right? So
right? So,
we know
we know
C1 will be equals
C1
to
will be equals to
N1
N1
N1 times
N1 times
unit distance,
unit distance,
right? Now here
right?
unit
Now,
distance
here
is
unit distance is
alpha, my
alpha,
lattice
my
parameter,
lattice parameter,
right? So
right? So,
N1 will be equals to
N1 will be equals
C1
to
by
C1
alpha.
by alpha,
Okay.
okay?
Oh no,
Oh, wow,
I made a mistake.
I made a mistake.
It's not
It's not
C1 by alpha.
C1 by alpha.
It is
It is
C1
C1
alpha times C1.
alpha times
So
C1. So
that's how it will be
that's how
equals
it
to
will be equals
number of
to
atoms per
number
unit
of
area.
atoms per unit area.
Volume
The
and this
volume
distance will
and
get
this distance will
cancelled.
get
So
cancelled, right? So
then 1 by 6
then 1 by
alpha
6 alpha
times
times
alpha
alpha
will be equals to
is equals to C1
minus C2.
minus C2.
Now we know from
Now we
differential
know from
equations
differential equations
C1 equals
C1
to
equals
C2
to
plus
C2
dou
plus
C by
dou
dou
C
x
by dou x
times
times
dx.
dx.
This
Or
dx
this dx
can be written as
can be written
alpha,
as
because
alpha. Because
that is my unit
that is
distance,
my
right?
unit
We cannot
distance, right? We cannot
go
go
below than that.
below
So
than that.
that dx can
So
be
that
written
dx
as
can be written as
alpha.
alpha.
So
So
C1 minus
C1
C2
minus
equals
C2
to
will be
dou
equals to
C by
dou
dou
C
x
by dou
times
x
alpha.
times alpha.
This will be
Then
equals
this
to
will be
1
equals to
minus 6
1 minus 6
jump frequency
jump
times
frequency
alpha
times
square
alpha square
times
times
dou C
dou
by dou
C
x.
by dou x.
And this whole
And
term
this
can be
whole
taken
term
as
can be
constant.
taken as constant.
That will be
That
equals to,
will be equals to,
this is minus not
this is
plus.
minus not
So
plus.
that will be
So
equals to
that will be equals to
J net
J net
will be equals to
will be equals
minus
to
D
minus D
dou C by
dou C by
dou x.
dou x.
So this is my
So this is my
very famous
very
and
famous
basic
and
equation
basic
for
equation for
flux.
flux.
Atomic flux. J
Atomic
net equals
flux.
to
J net
minus
equals to
D, where
minus
D is my
D, where D is
diffusivity
my
of atoms
diffusivity of
times
atoms
the
times
concentration
the
gradient.
concentration gradient.
Right? So
Right?
what are
So
the units
what
of
are the
my
units of my
flux? D
flux?
is
D
equals to
is
alpha
equals
square,
to
which is the
alpha square, which
distance,
is the distance, which is
meter square
meter
per
square
second.
per second.
Right? So
Right?
that is
So
my,
that is my,
and this is also
and
my
this is also my
Fick's
fix
first law.
fix first law.
Okay.
Okay.
Now
Now
moving on to
moving on
Fick's
to
second law.
fix second law.
Here
So
the
here
component
the
in Fick's first
in
law,
fix first law
we assume
we assume
steady state.
steady state.
How?
How?
Because C
Because C
is not a
is
function
not a function
of time.
of time.
C is not a function
C
of
is
time.
not a function of
C
time.
is only
C
function
is
of
only
x.
function of x,
Only function of distance.
only function of distance, right?
So that is
So
about this.
that is about this.
Okay.
Okay. Now,
What happens if the
what happens
concentration
if
is
the
changing with
concentration is
temperature?
changing with
Right.
temperature,
So that is my
right?
question.
So that is my question.
So for
So,
example,
for example,
if this is my
if this is my
concentration,
concentration
this is
and this
my
is my
distance, right?
distance,
So
right?
for example,
So, for example,
this is
this is my
C versus x.
C versus
Now
x.
it is
Now,
at
it is at
t equals to 1.
t equals to 1.
What happens
Now, what happens
at
at
t
t
equals to t2?
equals to t2?
This concentration
This
might change
concentration might
the
change
concentration
the concentration
versus x,
versus x,
right? Then
right?
what happens to
Then what
J1,
happens to J1,
the flux?
the flux?
How the flux will
How
change?
the
How the
flux will change?
concentration?
How the
How can we
concentration?
arrive to
How can we
basic
arrive to the
mathematical
basic
equation which
mathematical
will
equation
define
which will
how the
define
concentration
how
is
the
changing with
concentration is
time and
changing with
temperature?
time and
So
temperature? Sorry,
the time and
the time and
our
our
distance, right? So
distance,
how to
right?
arrive
So
that?
how to
Now
arrive
I'm
that?
going to
Now
derive
I'm
that
going
one.
to derive that one.
So
So
again,
again,
let me redraw
let
the
me
diagram.
redraw the diagram.
So this is my
So this
C,
is my C,
this is my
this
X,
is my X,
this
this
is
is
with time.
with time.
Let me,
Let me,
yeah.
yeah.
Now,
Now,
what happens?
what happens?
This is at
This is at
t equals to
t equals
t1.
to t1.
Now, what
Now,
happens at t
what
equals
happens
to
at t
t2?
equals to t2?
It may get
It may get
flattened out, right?
flattened out,
After certain
right?
time.
After certain time.
So,
So, right?
so
So,
this
this
is
is
my
your
C1,
C1,
C2,
C2,
C3.
C3, C4.
So how my
So,
fluxes are
how my
going to
fluxes
change?
are going to
Right.
change,
So if I
right?
draw
So, if I draw,
this for J,
it's for J.
let's say J is a
Let's say
linear
J is
function
a linear function for
for
now,
simplicity.
for simplicity.
So
Okay. So,
here I have
here
J1,
I have J1,
here
here
I have J2.
I have
Now
J2.
J1 minus
Now,
J2
J1 minus J2
is not 0,
is not 0,
right?
right?
because the concentration
Because
is
the
not linear.
concentration is not
If
linear.
concentration is
If
linear, then
concentration is
J1
linear,
equals to
then
J2.
J1 equals
The
to
flux
J2.
will
The
remain
flux will
constant
remain
throughout the
constant
distance.
throughout the
But
distance.
here it's not the
But here
case.
it's not the case.
Why? Because
Why? Because
concentration is also not a
concentration was
linear function
not
of
a
x.
linear
That's
function of
why
x. That's
there
why
is some
there
net
is some
accumulation.
net accumulation.
Accumulation. There
Accumulation.
is some
There is some
net
net
accumulation of
accumulation of
mass
mass
or
or
atoms.
atoms.
Right?
Right?
Now,
Now,
how
how if the time is if it is not
then
dependent on
J1
time,
minus
then
J2
J1 minus
will be
J2
a constant.
will be a constant,
Right?
right?
It might
It
it's
might
not zero,
it's not zero,
but
but
it is a
it
constant
is a
C1.
constant C1,
Right? Now,
right?
if it
Now,
depends upon
if it
time,
depends upon time,
right? If it's not a
right? If
steady
it's
state,
not a steady
then this
state,
C1
then this
will depend
C1
upon
will depend upon
time.
time,
Right? Again, this
right? Again,
equation
this
becomes more
equation becomes
complex,
more
right? Because
complex,
we are
right?
even
Because we
adding
are
the
even
term
adding
time.
the term
So
time.
now,
So now,
this net
this
accumulation
net
for a time
accumulation for a
dt,
time dt,
J1 minus
J1
J2
minus J2
for a
for a
accumulation time
accumulation time
dt will
dt
be equals
will
to
be equals to
the net
then
accumulation.
the net
How
accumulation.
much?
How much?
dc
dc
dou c,
or dou c,
because now c is a
because
function
now
of x
c is
and
a
t.
function of x and t.
Dou
So
c
dou
over
c
a distance,
over a distance,
let's say
let's
this
say
is dx.
this is dx.
Net accumulation
The net
over
accumulation over
here.
here,
Right? Now,
right?
this
Now
J1
this
minus
J1
J2
minus J2
divided by
divided by
dx
dx
will be equals to
will be equals
dou
to
c by
dou c by
dou t.
dou t.
Moving to the next
Moving
slide.
to the next slide.
Now,
Now
this is dx,
this is
right?
dx, right?
This is
This is
dx. The
dx.
distance
The
dx.
distance dx.
Okay?
Okay.
Now, we
Now
know again from
we know
differential.
again from differential,
J2 will be
J2
equals
will
to
be equals to
J1 will
or
be equals
J1
to
will be equals
J2
to
plus
J2 plus
dou j
dou
by
J
dou x
by dou x
times
times
dx.
dx.
J1 minus
J1
J2
minus
will be
J2
equals to
will be equals to
dou j
dou
by dou
J
x
by dou
times
x times
dx. Now
dx.
substituting
Now
that here,
substituting that here,
it will turn out to
it
be
will turn out to be
dou j
dou
by
J
dou x
by dou x
times dx
times dx divided by
dx
dx
will be equals to
will be equals to
dou c
dou c
upon dou t.
upon dou
This
t.
will get
This will
cancelled.
get cancelled.
So
So
dou j
dou
upon
j
dou
upon
x
dou
will be
x
equals to
will be
minus
equals to minus
dou c
dou c
upon dou
upon
t.
dou t.
Right now,
Right now,
dou c
dou
upon
c
dou t will be
upon dou
equals to
t will be equals to
this is j.
this is j.
We know from fixed
We
first
know
law
from fixed first
j
law
equals to
j
minus
equals
b
to minus b
dou c by
dou c by
dou x.
dou x.
Right now,
Right now,
substituting that here,
substituting that here,
minus
minus
dou
dou
differential
differential
of
of
x
x with respect
minus
to
d
x minus d
dou c
dou
by
c
dou x.
by dou x.
Now,
Now,
there are two cases
there
here.
are two cases here.
Case 1,
Case one,
if
if
d
d
is not a function
is
of
not a
x,
function of x,
okay,
okay,
then
then
this will
this
come
will
out, it's a
come out,
constant,
it's a constant,
then
then
dou c by dou
dou
t
c by dou t
will be a much
will be a
simpler
much
equation.
simpler equation.
Dou square c
Dou square c
by dou x
by
square.
dou x square.
Now if
Now, if
case 2,
case 2, if
if d
d
is not a function
is
of
not a
x,
function
is a
of
function
x,
of
is a
x,
function of x,
then
then
dou c by dou
dou
t
c by dou t will be equals to
minus
minus
dou by dou x.
dou by
I'm
dou
writing it
x. I'm
again,
writing it again.
minus
Minus dou
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 c
c
by
by
dou x.
dou
So
x. So
we will do
we will
differentiation by
do
parts.
differentiation by parts.
So
So
dou
dou
d by
d
dou x,
by dou x,
it will become plus
it will become plus
times
times
dou c
dou
by
c
dou x
by dou x
plus
plus
d
d
dou square c
dou
by
square c by
dou x square.
dou x square.
Now if you assume
Now,
d
if
is
you
only
assume
function
d is
of
only a function of
x, then
x,
this
then this
partial derivative can
partial
be
derivative can
converted
be
into
converted
exact
into
differential
exact differential
dou d
dou d
by dou x,
by dou x,
right?
right?
So
So
c is a
yes,
function
c
of
is a
x
function of
over t.
x comma t,
x comma t,
x comma t,
x comma t.
x comma t.
Right? Now
Right?
this is for
Now this
only
is for
ideal
only
cases.
ideal cases.
Now we
Now
know
we know
that
that
if
if
we all know that
no, we all
uphill
know that
diffusion and
uphill diffusion
downhill
and downhill
diffusion.
downhill
So now,
diffusion. So now, so
this is my g was
this is my
x
g was
and this is my
x and
curve.
this is my
So
curve.
if I
So
have
if
two
I have
compositions
two
here,
compositions here,
xa1
xa
and
one and
xa2. So
xa2.
what
So
I'm going to do,
what I'm going to do,
I'm bond this
I'm bond
two
these two
compositions.
compositions.
So they will
So
arrive
they will
to a
arrive
minimum
to a
composition
minimum
xa0.
composition xa naught,
So
right?
here the
So
composition
here
will
the
get
composition will get
xa0.
xa naught.
Then when you heat
And
it
then when
and
you
the
heat
atoms
it and the
start to
atoms
diffuse from
start to
here to
diffuse
here.
from here to here,
Right? Now what
right?
happens?
Now what happens?
Now what if I'm
Now
having
what if I'm having
immiscibility?
immiscibility,
Right? Like this.
right? Like this.
So if I have a
So if I
compositions
have a
like here,
compositions like here,
right, then what
right?
happens?
Then what happens?
So if I'm trying
So
to
if
mix
I'm trying to mix
these two phases,
these
they
two
will
feathers, they will
try to come
try
down
to come
to this
down
point.
to this point.
Here we have a
Here
common
we have a
tangent.
common
This is
tangent.
my
This is my
composition. Right
composition.
now, what
Right
happened? It
now,
is a
what
downhill
happened? It is a
diffusion
downhill diffusion
because
because
suppose
suppose
the A will
the
get
A
richer in
will
A.
get richer in A.
Suppose this
Suppose
A
his
will get richer
the
in
A
A.
will
We
get
have two
richer. We
components A
have
and
two
B.
components A and
So
B.
A will richer
So
in
A
A,
will richer in A
B will get
and
richer
B
in
will
B.
get richer in
So
B.
there is
So there is
separation of phases.
separation of
This
phases.
is not
This is
ideal
not
case for
ideal case for
fixed
this
first law and
fixed
second law.
first law and
So
second law.
there
So there
we apply
we apply
J equals to
J equals to
minus
minus
M
M
B
B
dou mu
dou
by dou
mu
x,
by
where
dou
mu
x, where
is my
mu is
chemical
my
potential,
chemical potential.
where M is my
Your M
mobility.
is my
So
mobility. So
this is I,
since I,
right? So
right?
yeah,
So yeah,
that is about
that is
the
about the
flux
flux
in terms of chemical
in terms
potential.
of chemical potential.
Now,
Now,
so that is
so
all
that
about
is
today's
all about
session.
today's session.
We have
We
covered
have
diffusion
covered diffusion
and
and
little bit pieces of
little bit
diffusion,
pieces of
and then we
diffusion, and
arrived
then
to
we arrive to
yeah, this is all
yeah,
about
it's
diffusion,
all about
and then we
diffusion,
derived
and
this
then we derive
delta G,
this
the excess
delta
free
G, the
energy
excess
for
free
the
energy
formation
for
of
the
new
formation of
surface,
new
right?
surface,
So
right? So
this is about that,
this is about that,
and
and
and then
and
we
then
derived
we derived
how the composition
how
will
the
change with
composition will change
temperature,
with temperature,
and this is free
and then his
energy
free
curves,
energy
free energy
curves, free
composition
energy
curves for
composition curves
different
for different
invariance reaction.
invariance reaction, right?
So and
So
then
and then
we derived for
we derived for
Clash-Whisper-Apron
Clash-Whisper
equation, and also
equation,
gave
and
an
also
example
gave
how
an
to
example how to
derive the
derive
whole
the whole
equation,
equation,
and then the
and
Gibbs-Weiss
then
rule.
the Gibbs-Weiss rule.
So
So
that's all for today's
that's all
session.
for today's session. And
Thank you, and if you have
thank
any
you. And if
doubts,
you have any
please
doubts, please
ask now,
ask now,
or else you can leave the
or else you
session.
can leave the session.
Thank you.
Yeah, thank you.